Hello. Please, good morning. Good morning, everyone. Welcome for our second day of the plenary meeting of the 8th General Assembly of CAMS. It was good. It was good to have you all yesterday evening for this nice reception for the 10-year celebration. It was very nice, but we still have a working day, so we have to work now, and we will have a busy day. This morning we will review the main achievements, main results of the work carried out during the years in the various services. So we will chair this session with Maria Bertald from DG Defis and Richard. We will start with a review of the global services and then the solar radiation service, and after the coffee break, in between, we should have a new group picture. So Francesca will tell us before the coffee break. And after that, we will review the regional and policy services and the emission and fluxes services. So we are a bit late, so let's start immediately. And I would like to give the floor to Johannes Fleming, who will present the progress of work on global monitoring and forecast. Please, Johannes.
So good morning also from my side. It's a pleasure to be the first speaker in this session. I give you a short update about the global system. This is an effort where many people are involved. Maybe the most important one are the colleagues from ECMWF and the colleagues from the CAMS 235 colleague, the contract led by Vincent Heunen and Samuel Remy. So between the three of us, we co-authored this talk. But the list of people contributing is very long. Also the emissions, the verification, so it's not an exclusive job. Because it's the beginning of this session, I show maybe the most popular slide at any of the CAMS assemblies, showing the overview of the CAMS system. So we see the global CAMS system, which is run at ECMWF, and we see the cluster of the regional models over Europe. We see the various input data that are required, the emissions, and also the observations which are used in data assimilation procedures to improve the quality of the forecast, namely satellite observations for the global system predominantly and in situ observations. So what are now more precisely the global products from ECMWF? We have the IFS Compo suite, which is run at a 40-kilometer resolution and which predicts and does monitoring and data assimilation for aerosols and reactive gases. About 20 satellite retrievers are being actively assimilated of the various species which are listed here: ozone, NO2, AOD, carbon monoxide, volcanic SO2. And then we provide 2 times a day a 5-day forecast of the atmospheric composition. We also provide, which is of interest for people interested in satellites, specific plots that show the relation between the satellites that we use and monitor in our system against the O-suite, and that's, I think, very important information to see how different satellites agree for the atmospheric composition observed at a certain time. And then next to these operational forecasts, we also have auxiliary experiments which run more in a research mode, which help us to better understand how good we perform in various aspects. One control run doesn't do any data assimilation, so it's just of atmospheric composition, so it's just a model forecast, and comparing this run against the operational product can help us to understand the impact of data assimilation on our forecasts. And then we have a second research type run in which we don't use prognostic aerosols and ozone in the radiation scheme, so that's what we do in our operational products, and this can help us to understand the impact that aerosols and also ozone have on the weather forecast, which is of course a topic which is of high interest for ECMWF, which is a provider of numerical weather prediction. So that's the Compo suite, as we call them. We also have a GHG suite, which has 2 different resolutions, it runs it. There's an analysis which runs 4 days behind because of the availability or the delayed availability of the satellite data that are being assimilated, and then a forecast at a much higher resolution as we do in COMPO at 9 kilometers over 5 days. And just to provide you with a complete picture, I also mentioned here the GFAS fire emissions which are produced by ECMWF on a daily basis. So this is just what I mentioned before, an advertisement of these monitoring plots. There's the website here, and I just selected here the TROPOMI products, which we to a large extent already actively assimilate in our system. Some of them we also just passively monitor, but you can go to this website and then see immediately how the satellites observe things and also how they are positioned themselves in relation to our products. What I show here are the first gas departures. Now, when we develop the cycle for the operational system, we follow what is suggested by ECMWF for the development of the NWP cycle. So about every year we have an upgrade, and in this graph I wanted to briefly describe the procedure, how we do this. So before we do this upgrade, there are several developments going on in the different groups. We have aerosol developments, chemistry developments, on the modeling also GHG developments. In parallel, colleagues at ECMWF work on the data assimilation, and sometimes we also update the emissions. And what I want to highlight here is that these developments sometimes cannot be fully synced. So some model develops don't know about the new emissions, or the data assimilation does not know about model developments and vice versa. So at a fixed point in time, everything has to be together, and then we start the cycle preparation. So everything is then combined into one system, and in a relatively short period, we run different versions of this next upgrade, the O suite, where we change different aspects, and we always evaluate these runs in a very sort of routine-like manner to decide, is this upgrade an improvement or not? And during this process, we do, of course, fixes to the data assimilation and to the model, but they are not meant for major developments. And at the same time, we also have the impact of the upgrades of the NWP. So it's quite a lot of things that come together, and it's sometimes difficult or challenging to really come up with sort of the optimal solution. And then there's a fixed point in time where we have to be ready, and we provide our system to our colleagues in the operations department or in the forecast department, and then they start what is called an E-suite. So that's a sort of a test of the O-suite for a specific period. And then the evaluation of CAMS 285, the project led by Henk, kicks in, where they look in a lot of detail into the results of the O-suite, and if the results are satisfactory, we will follow the general implementation together with NWP on a certain date, and then the operational system starts. So talking about this new cycle, what are the major upgrades in 49R1, which will be implemented in October this year? 49R1 is not such a big upgrade as the previous cycle, where we added stratospheric chemistry, but we still have a lot of sort of stepwise improvements of the modeling system, also of the data assimilation. In terms of the GHG system, it's worth mentioning that we have now the Farquhar photosynthesis model included, and we also have wetland methane emissions. Another novelty is the addition of the TROPOMI methane assimilation in the system, and we also upgraded the background errors following the approach for the EDA. For the aerosol model developments, maybe the most important one is that we have now a better description of stratospheric aerosols, which I will explain you in a minute. But there are further upgrades, and this is just for reference. So showing you this GHGO suite, which runs operationally only since the spring this year. What we see here is the general flow structure of this experiment. So previously, we only assimilated Yasi and GOSAT. They are put into this analysis at a resolution of 25 kilometers, 5 days behind, and then we make a forecast from there, and then in a relatively complex procedure, this analysis or the forecast from this analysis is being merged with the high resolution run in order to maintain the granularity of the high resolution, but also to benefit from the analysis that we have in the observations. And the upgrade, as I already mentioned before, for 4901 is the addition of Trobomi. This is the slide summarizing the progress for the stratospheric sulfate. So we have, as you know, the Basque scheme, and sulfate is represented there, but we managed to link the sulfate production in the stratosphere to the chemistry scheme, and by doing this we get a better description of the processes in the stratosphere, and this has been tested for the case of a major eruption, which is shown in the plot below. We see here the decay of stratospheric sulfate as seen in the observations from the Pinatubo eruption, and then in blue the curve as we model this with this relatively simple but effective approach. Now I wanted to, in this talk, highlight a little bit more this evaluation that we do as part of the cycle development, because I think that's a discussion that we can have within CAMS. What are our priorities for this? Because in the end it will change sort of what we consider an improvement, what aspects we want to improve. So the data that we use for the in-house ECMWF evaluation is shown here. We use air quality observations over Europe, we use air quality observations over China, and we also have data from the AirNow network, which is mainly data over North America, but also some data around the world. But overall, you see in this plot that we have also a lot of gaps. So it's, for instance, about Africa, South America, we don't know anything about, in our evaluation, about the state of the air quality, and we also don't check our model in those regions, which I think is something we could work on. For Aeronet, which is the AOD observations, we have a better coverage, but still several areas are not covered by this. And then on the side here where I show you the position of the ozone zones. Also here in certain areas over Europe and North America, there's relatively good coverage, but in other areas we don't have a lot of observations. So, as I already mentioned, the spatial coverage is sort of a challenge, but there's also another challenge which we can think of is what kind of statistics we use. So far, we mainly focus on mean sort of typical statistics like bias and RMSE, but I think it would be nice in the future to really have a more user-driven or application-driven verification. So we should test whether it's worthwhile to look at the exceedances of thresholds rather than just the mean values. But we also need to do this, of course, in a sort of standardized manner to be in a position to easily compare different runs and to can say this version is better in predicting higher values than this one. So some solutions are, of course, to use more observations, and in CAMS 282 they have more observations, and it would be probably better if we can also use them. And also what I think is interesting to learn from the NWP colleagues, what they do. So in NWP, they have a clear advantage compared to atmospheric composition because they don't need to rely on entirely on observations, in situ observations. They use mainly the analysis, so the gridded gapless field which is a combination of a model and satellite observation and other observations as a reference. And once you do this, you don't have any problems anymore with spatial coverage. You can always compare the full fields, and this gives you a lot of advantages. Normally, our trust in our analysis is not so high that we think they could be considered as references, but I do think for certain fields like AOD, that's already the case. So we are certain that our AOD fields or analyses are a good representation, and we can start this machinery to evaluate the forecast with respect to the analysis. And I have done this using the infrastructure at ECMWF, and what you can see here is a verification against the own analysis, comparing the older cycle 48R1 and the new implementation of 49R1. And on the top graph you see for the southern hemisphere, for the tropics, and for the northern hemisphere, the increase of RMSE with lead time, and we can see that 49R1 has sort of a smaller increase, indicating that the forecast quality is indeed better. Talking of NWP, another sort of information source which we try to use is to look into the impact of aerosols and ozone on the weather forecast, and maybe to make indirect assumptions about our fields. And this is shown here on the left-hand side from your perspective. What you see in these little stem plots here are vertical cross-sections of the differences between the RMSE at different lead times, going from the top to the bottom to 5 days, against the analysis between 49R1 and 48R1. And in areas where we have a bluish color, the RMSE has been reduced, and this is an improvement. So these plots need to be looked at. We want to have as much blue as possible. And when we looked at the NWP verification of 49R1 for the first time, we saw a lot of blue, but also over the southern hemisphere, there was a sort of large area where we got a degradation. And after looking into this in more detail, we could trace this back to an accumulation of black carbon and organic matter in this area, and the sort of the area around the edge of the Antarctic peninsula, Arctic area. So it was an indication that something is not right with our aerosol fields, which we would not have detected otherwise, because we don't have observations in this area. And by changing the modeling aspects that led to this accumulation, we could remove this accumulation, and in the plot in the middle you can see now these scores, which are as blue as we expected them to be. So how good is the CAMS model? I think one important aspect to answer this question is to compare it against the other centers who also do air quality forecasting. And within WMO and GOR, there's an initiative called JAFIS, which focuses on air quality forecasting, and we start to prepare intercomparison efforts. And one of these efforts, which has been going on for a long time, is between different global and regional models over North America, carried out by the colleagues from Environment Canada. And every quarter they provide a report of the performances of the different models that are listed here. On the left-hand side, you can see the long-term performance for ozone, NO2, and PM 2.5, and the green model is ECMWF, so we are often but not always on top. The performance quality is also summarized in tables like this. This is the one from the last report from Q1 this year, and we see ECMWF is actually, according to this statistic, producing really the best ozone forecasts. For NO2 we are also green, we are quite good, and for PM we are also leading the bunch. And if we go back to a season, July, August, September last year, where we had really a lot of wildfires over North America, we see that ECMWF, the CAMS model, really outperformed all the other models. So I think that's something we can be quite proud of, and that's the end of my talk. Thank you.
Thank you, Johannes. I was about to tell you 3 minutes, and that's perfect. Thank you very much. And so there is time, because Johannes has 3 minutes, to answer a burning question, if there is one. We will have a kind of discussion after all the presentations, but if there is really one question that you would like to ask to Johannes after this nice presentation, very comprehensive, no? No? Okay. Okay, thank you, Johannes. And the next talk will be given by Ines, and Antje will talk about the reanalysis part of the work. Thank you.
Laurence, I hope you can hear me. If I could have my presentation, please. So I want to thank Johannes for setting the scene really nicely for a talk about reanalysis, focusing on all the changes we do in our near real-time system, because we always work to improve it and have new model cycles every year. While this is really great if you want to use our near real-time data, our forecasts, it makes it really difficult to compare this year's data with last year's, for example. So if you want to look at anomalies, if you want to look at trends, you can't do that with our near real-time system, because you might just be picking up changes, for example, in the chemistry, changes in the emission data sets we use, or changes in the data we use. So what we do from time to time is we take one version of the model and go back in time and run a whole long period with that one version of the model. And we usually go back to 2003, so to the beginning of Envisat data, and then also Aura satellite data in 2004, and try to use as many reprocessed, consistent observation data sets that we can find for this period. So we use consistent observations if possible. We try to use consistent emission data sets as possible, and we keep horizontal and vertical resolutions the same. So we try to produce a consistent data set that you could use for trend analyses or to look at climatologies or anomalies. And the plot on the left illustrates this. So we are looking here at an ozone score comparison against ozone sonde data at the Antarctic Neumayer station. So it's a time series. Values at the top are good scores, values at the bottom are bad scores. And in black is our near real-time system. So you see, when it started in 2009 or so, every year during the ozone hole we have these large or very low peaks. So the model always struggled and we had really bad scores. We then improve with time. But if you compare that to the red curve, which shows the same score from a reanalysis, you see we're much more consistent in time. So it's really good to go back and produce a consistent data set. And we've done that, so we've produced the CAMS global reanalysis, which now covers the years from 2003 to 2023. And we keep this going, so we add new data roughly every 6 months. It has a horizontal resolution of 80 kilometers, 60 vertical levels, and we have 2 products. We have one reanalysis, which we call EAC4, which gives us aerosols and chemical species. And then we have another one that gives us greenhouse gas information, so CO2 and methane, which we call EG4. And all these data sets are available freely from our atmosphere data store, the ADS. And there's also various reference papers available online, and also validation reports produced by the CAMS 282 project. So the model cycle we used is 42R1, so it's quite an old one, and we started production of this, I think, back in 2017, so it's about 7 years old. We used the version of the CB05 tropospheric chemistry scheme, and we used the Cariol decay scheme for stratospheric ozone. We used the ozone and aerosols from the reanalysis interactively in the radiation scheme. And this is one example of validation plots we can do. This is done, again by our validation project, CAMS 282, and is available from the Aeroval server, which you heard a lot about in the recent days. So here we compare against AeroNet observations, and we're looking at a bias. So the top plot shows a global mean bias. The orange curve is the reanalysis, and you see while there's some seasonally varying bias in AOD, it is really quite consistent over the whole 21-year period. We also have a control run for the reanalysis where we don't assimilate any atmospheric composition data, and that's the light blue curve. So you see there's differences between that and the reanalysis, but also it is quite consistent with time. And then if you zoom in on the most recent years, which is shown at the bottom, where a time series starts in 2013, you have more curves. And here the red one is our near real-time system at the time. And you see while the analysis is actually not that different for AOD compared to EAC4, the control run, so the run that just shows us our model performance, is very different. And you see much larger biases at the beginning. So you see that the model improves with time, as Johannes already showed for our most recent cycle, being an improvement compared to the previous one. And so you see the biases reduce, but you also see you have a much better consistency in the EAC4 and its control run. And then a data set like the reanalysis can then be used, as I already said, to look at trends and anomalies. And we do that by contributing, for example, to the BAM State of the Climate reports that are published every year. And we contribute to various sections. We contribute to carbon monoxide, to aerosols, and also to the fire section. And the plot at the bottom right shows a comparison of CO from the reanalysis with TCON data at Park Falls. So the data are in the black dots, and the line is the reanalysis. And you see that not only do we get the seasonal cycle right, we also get this trend towards lower concentrations with time. And so that is really nice and gives us some confidence in the product we produce. The other plots show AOD anomalies, the two on the left, for different periods. And you can see in the blue colors, there's, for example, a reduction of AOD. This is the trend, so a trend towards lower AOD over China, over Europe, over North America, and an increase over India. And then the plot in the middle at the top shows extreme aerosol days in 2021. And the red colors in the Northern Hemisphere show you that that's mainly related to wildfires and transport from the wildfires into the Arctic. So we can use our data set to look at cases or events like this. So we use a whole lot of observations. In our reanalysis, we assimilate data for ozone, for CO, for NO2, and for aerosols from a range of satellites. And here I show a time series of the various data sets, atmospheric composition data sets we assimilate. So I guess you won't be able to read all the details, so don't worry about that. What I want you to take from this is that there's a lot of changes in the observing systems. So for example, here we have Envisat AOD. So Envisat is there at the beginning, but then it dies in 2012. So the satellites come and go. We have various SBUV data that come and go and make a long record together, but there are a lot of changes. There are a few data sets which have been very important for us, and I've pointed them out here on the right. So it's the MOPID CO, which is the only CO data set we assimilate, which have been there all through. MODIS AOD is a data set we've assimilated all the time. And then MLS ozone came in I think, August 24, and is very important for our vertical ozone distribution. So if any of these instruments go, there will be no point continuing this reanalysis, because whatever we get afterwards will be very, very different. Also, I think we started the production in 2017, so at some point we caught up with near real time. That meant we couldn't use the reprocessed data anymore, and we changed to using near real-time data. And we keep running shortly behind near real-time now. And that also led to changes. And some of these changes are shown here. Here, again, this is from the validation report produced by CAMS 282. And I'm showing ozone biases against ozone sondes. So if you just look at the top 3 plots, which show 3 different areas, so it's time series from the beginning of 2003 to the end of 2023, and the black line marks the location of the tropopause. So you see, in the stratosphere, actually, the biases are very similar every year. So that is a good data set after the start of, say here, MLS. So the first years are a bit different, but afterwards this is really quite consistent. But there's a lot more changes in the troposphere. So tropospheric ozone in our system is a lot more affected by instrument changes. And another point I want to make is that it is very important to have good emission data sets for our reanalysis. So in the CAMS reanalysis EAC4, we used the MAC-City emissions, but they were only produced until 2020. So since 2020, we've been running with the 2020 emissions, because if we changed to the CAMS GLOB emission, it would be a huge change because they are so different. And this you can see here very nicely, because we get an increasing bias in NO2. This is comparison over Europe against NO2 surface data after 2020, because the emissions just don't give us the correct trend, because we just run with the 2020 emissions. So for a reanalysis, it is really important to have, both for observation data sets and also for emissions, continuation of whatever data set we are using, because if we change, we introduce changes in our data set. And then I just wanted to also highlight that we have a greenhouse gas analysis, EC4, which is also available from the ADS. The original data had increasing biases after 2019 when we changed to the near real-time observations. So we've done a rerun from the end of 2018 onwards, which looks better and has been evaluated now, and which will also now soon be available from the ADS. So if you want to use the greenhouse gas data after 2019, it's perhaps worth waiting for this one and have a better data set. So we are keeping this reanalysis going, but it is getting more and more difficult because of changes in the observation system, the emissions that are not appropriate anymore. We use an old model cycle. So NWP often introduce new instruments into the ECMWF system, but the old model cycle can't handle them, so we are losing more and more instruments, using less and less data. So it's getting more and more difficult. And as I said, these key data sets, once they go, there won't be any point. So what do? We go and produce a new reanalysis, which we will call EAC5. And preparation for that has started. We are going to go back to 2003 again and run from there, but we are now using a newer model version. So we will use pretty much the cycle that Johannes has introduced. So we have the IFS Compo-Bascoy scheme, giving us tropospheric and also now stratospheric chemistry. We have, we'll use the model cycle 49R2, which is the same that ERA 6 will use. So we can benefit from all the work they do on the meteorological side. We'll increase the resolution to 137 vertical levels and to about 40 kilometers in the horizontal, so double that. And we'll use new reprocessed observations and new emissions, including hopefully some online biogenic emissions. And currently, we have acquired most of the data, but we still have to process quite a few of them, which is a huge task. And we are testing the model configuration. So, we don't include emission inversion in this reanalysis yet. And the plan is to start production in the first quarter next year. So I just want to show one time series. This shows some of the new data sets that we are going to use and that people in our forecast department are acquiring and processing, just to illustrate that this is not something you do really quickly. You can't just say, oh, let's run another reanalysis. There's an awful lot of effort from a lot of people going into this. And then, we want to this time spend a bit more time looking at the data sets before we actually start running. So we now have a tool that allows us to work directly with the buffer files that we use to feed data into our system, so we can compare instruments before we start to make decisions about bias correction and see how consistent various data sets are. And this is just one final slide to show we will now have stratospheric chemistry species in the reanalysis. To summarize, we have the CAMS reanalysis for aerosol and chemistry and also for greenhouse gases from 2003 onwards. They're both available from the ADS, and also the EG4 rerun will be available soon. We have a lot of validation reports for the reanalysis as well as all our other products on the website, and we will start a new reanalysis production next year. Thank you.
Many thanks, Andrew, for this very comprehensive presentation. Very nice. I see two questions. We will take both. So, yes, Thomas and Augustin, please.
Thank you very much for this brilliant overview of the reanalysis. You have not said a lot about extending the history further before 2003. As you know, this is a repeated user requirement, so can you please elaborate a bit on this?
The problem is that the further you go back in time, the more difficult it is to find observation data sets. So we go back to Envisat. Before that, I guess we could perhaps do aerosols going back further in time, and perhaps also ozone. But the other ones would be incredibly difficult. So we are aware there is demand, and we have considered it, but we thought it's just going to be too difficult. So it's perhaps worth for the next phase to think about at least doing some aerosol ozone, or seeing if we can incorporate that in some ERA 7, because if that doesn't need the complete chemistry, it'll be cheaper to run, and then it could be part of that, perhaps. But it's a good point.
Yes. Augustin, please.
Yes, thank you. And it's very lot of inspiration for us at the regional scale if we were one day to engage in doing a proper analysis going back in time, so which we are not really doing at this stage. And I think there are indeed, again, a lot of user expectations, especially for impact studies. If you want to assess the effectiveness of policy in Europe, we mentioned a couple of days ago also the impact on health, the impact on agriculture. For all this type of impact study, we really need to have a regional scale analysis at some point. But one difficulty we are facing is this consistency of the data set in time. If you look at the EEA type of observation in Europe, it increased a lot, especially if you compare before 2010 and after 2010. We are basically talking about a factor 3 in the number of stations, and also you have some countries that are basically popping out, so just starting to report in the database. So very inconsistent coverage over time. So I know you have access to a more consistent data set, but if you were in a position to assimilate these European stations before and after 2010, what would you do?
It's difficult to say. Perhaps could you leave some of the later ones for validation and make sure you have a consistent coverage? Might be one idea. Or otherwise go back to 2010, then at least you still have a long data set.
But you will still use a consistent data set. You will not use as many observations as you have access to.
It's a very difficult question because we also have that for our reanalysis. I mean, my personal opinion is users want a consistent data set. They don't want the best possible data set, say, in 2008, and then a worse one in the other years from a reanalysis.
Yeah, but one country in Europe might say, I started monitoring and reporting to EA in 2015, and I want the situation in my country to be reflected appropriately in the CAMS analysis.
Yeah, so it's difficult. We have the same with tropomi data coming in 2018, which we will use because it's Copernicus instrument and it's very important to use, but it will introduce a change in the new reanalysis. So, yeah, I can feel with you there. Thank you.
Thank you very much, Andrew. Next presentation will be given by Henk Eske from KNMI, and we will go deeper in the evaluation processes for the global products. So please, Henk.
Thank you. So can you hear me? No. You can still not hear me? You can hear me now, I think, huh? Yeah, now it's better. Okay. Yeah, so the slides are up. So Johannes and Antje already gave a lot of advertisement for the work that we do, so I'm wondering a little bit why I'm standing here, because already a lot has been said. The green button is forward, eh? So I will talk about the EQC activity for the global outputs. Oops, what's happening? Can I go back also? Yeah. Yeah, so my name is Henk Eskes. I'm working at KNMI in the Netherlands, but I want to highlight, I didn't list all my co-authors, but in fact this is really a team effort. We have 12 partners in the contract, and some 20 people are really actively contributing to this work. So I didn't list all of them, but clearly you have to realize there's a lot of work behind this. So I split up my talk in two parts. So first of all, I will give you a general overview of what we do. And then secondly, I will talk about the innovations in the past year and what we have been developing. And we are constantly innovating and showing what we did recently. Okay, so what do we do? So we take the CAMS products, so basically we take the data that you can also download from the ADS, and it's an a posteriori activity, so we look at the data sets that are available for the users, and we compare them with as many independent observations that we can find. And that's quite a diverse data set, so that's shown here on the left. So we look at data coming from the surface. So we have, of course, for instance, the regulatory networks for air quality, looking at air quality at 3 kilometers or 3 meters altitude. But we also have a lot of remote sensing observations from the surface. And one spectacular one is shown here. That's laser beams which shoot into the stratosphere and measure stratospheric profiles of ozone. But then also other platforms like balloons, the ozone sondes. We use routine data from aircraft and also satellite data. So it's a very diverse set of data sets that we use. And clearly we want to make use of all the efforts that are there to harmonize these data sets and to so all the networks which sort of collect these data, make sure that they're quality controlled and in standardized formats. So that's the WMO GAW data sets, ICOS for greenhouse gases, IAGOS for this routine airplane observations, NDAC, sort of background stations all over the world, originally for the stratosphere, but now extending also into the troposphere. Actris, which has been discussed during the meeting here. Aeronet, that's for the AOD. It's a remote sensing of AOD and quite an extended network, very important for us. And then also things like EEA, EMAP, and also other, so the American and the Chinese data sets. Oops, yeah, so the gases that we target are already mentioned by Johannes, for instance. So we have basically all the prime targets of CAMS are also evaluated. So for gases we have ozone, CO, there's a lot of focus on those two. But also the short-lived gases, NO2, formaldehyde, SO2. And we more recently started to look at the stratosphere. For aerosols, we look at the radiative properties, aerosol optical depth, angstrom exponent, but then also particulate matter measured at the surface, so PM10, PM2.5. And for greenhouse gases, we look at CO2 and CH4, total column, surface concentrations, but also profiles where we have them available. In total, we deal with about 65 observational data sets, so it's quite a big effort and quite some work to do that, and that's also, I guess, the reason that we have quite a big team to work on this. Yeah, one point here is that for us it's important because we really want to evaluate the near real-time products of CAMS. We also need observations in real time. And for us, a deadline is something like 1 month after sensing, because then we can still incorporate them in our validation reports. So therefore, the CAMS in situ contracts are also very important for us, because they make so that's also dealing with this near real-time availability of data sets and harmonization of the data sets. Good. What do we produce? We have a series of validation reports. One main report is the evaluation of the CAMS near real-time service. We do this on a 3-monthly basis. So every 3 months we produce a report like this. The last one goes up to February this year. And the reason for doing this every 3 months is, as was already mentioned, the CAMS system is really a moving target. So there are at least once a year we have this upgrades of the CAMS system, and things will change when we have the upgrade. And that's clearly shown here in this graph. So this is CO column evaluations with the NDAC F-tier observations. And you see a timeline here of 8 years, and the vertical lines, the black lines that you see, are the different upgrades of the CAMS system. And for instance, in the last upgrade, the 48R1, you see that there is a change of behavior. And so it's very important to really be up to date with the validation reports to capture the information for the latest version of CAMS. Then we evaluate the reanalysis. That has been mentioned clearly. So the EAC4 and the EC4, that's why there are two reports there. And there, this plot has already been shown by Antje, so we really focus on the stability of this reanalysis. And Antje said that this is a main target, to have really a consistent long-term data set. And you can see that, for instance, for AOD, we have quite a stable data set. We describe quite well the seasonality and also the trend in the AOD with that reanalysis. And then we also look at upgrades of the CAMS system. So, sorry. The latest big upgrade was this cycle 48R1. So that was really a major a change in the model. So it was collecting a couple of years of development, linked to also the move to the new Bologna supercomputer. And there the main question is the upgrade performing better against independent observations? And to summarize this, we make these kind of scorecards where we list all the different comparisons that we do, and then look at, so we have on the top we have the aerosols, and below that we have the reactive gases. And then we sort of report a relative score, showing if the new system is really performing better against independent observations than the old system. And what you can see here is that this upgrade was really quite successful. most of the colors are green, or they are neutral, sort of white, so we don't see much difference. And there are a couple of examples where, again, certain data sets we see a bit of a degradation. But overall, it has been a really successful and very, exciting upgrade. So, apart from this, we also work on routine display of validation information on websites. And in fact, we have developed two validation servers. And the links for the two servers are given down there. So there is the evaluation server for the near real-time data from CAMS. That's this global evaluation server. And then we have a new server based on the Aeroval, which was discussed a couple of times already during the meeting. That's this, and this has now a new URL, this global EQC server. And these are really meant for you to explore the data sets and to look, for instance, if you're interested in a certain country, you can go to these maps with all the observation locations. You can pick your own favorite station and display the time series of the evaluation and get information locally on what kind of scores CAMS is giving. So there is really a very rich data set behind it, some 60 independent data sets, which we support here, and going from surface data to profiles to satellite data and all kinds of time series and also overview statistics. Okay, so that's roughly what we do. So what's new? What have we been working on in the last year? One thing that we did is we revisited this Cycle 48R1 because this is such an iconic upgrade of the CAMS system. We thought it would be nice to write really a paper about this, and this has now been accepted and will soon be online in its final form. So we looked again at all these data sets. We extended the time period with 3 more months that we had available after some time compared to the report that we wrote originally. And so the paper is also sort of giving an overview of how we work and what we do and what kind of data sets we are working with. So if you're interested, please have a look at the paper. A second thing, which is quite new for us still, is because with 48R1 we have this stratospheric composition information. So we have all these trace gases in the stratosphere which are now new. And we have also extended our validation activity, and this slide is showing that in some details. So the different things that we look at now for the stratosphere are ozone, clearly, but also things like water vapor. We look at long-lived tracers, greenhouse gases, N2O, methane, but also clearly the CFCs, which determine the breakdown of ozone. And then also short-lived species like NO2, and also the CLO, which is important for the breakdown of ozone in the ozone hole. And so the small boxes there give a bit of physics here. So what we see, for instance, is that water vapor shows an underestimation, and we link that to the Hungatunga eruption, which was bringing a lot of water vapor into the stratosphere. So at the moment, within the CAMS team, we are looking if we can maybe account for that in the next reanalysis and see if that can be improved. For the long-lived tracers, the profiles look really nice, I would say. So it's really showing that the tropospheric sources and the loss in the stratosphere is quite well handled with the new stratospheric chemistry. For N2O, we have these overestimations above 10 hectopascal, so that's showing one aspect where model development can help, and something that may be improved in next versions. And then also the chlorine activation is quite well captured by the new BASCO chemistry. Okay, Aeroval. So there's a lot of development going on on this, especially this second validation server that we are now developing. Has been discussed already a couple of times. So it's has a very nice interface, giving you a lot of flexibility to look at individual time series, but also regional averages, statistics for regions. So it's a very exploratory tool and very flexible and also very responsive. So I would really encourage you to have a look and explore the data sets which we provide on Aeroval. Recently it got a new URL, so that's this global EQC server, and also there is a CAMS news item on Aeroval that you can consult. Under the hood, the Aeroval and also the PyAerocom pre-processing of all these data sets has been really redesigned, and to make it much more flexible. For instance, the inputs, so we have now a set of PyAero readers, as they are called, so they're supporting different data sets, but also making it more flexible to add new data sets. An interesting thing for me is that PyAerocom is now also supporting these collocated data sets, data objects, and that's, for instance, very interesting for NDAC. So instead of providing model data, model fields and measurements separately, we provide the measurements plus the model collocated values together. And for much of the NDAC data sets, we have quite complicated observation operators, so including averaging kernels. So those things can be provided, for instance, by Bavo from NDAC, and then fed into the system. There's a lot of activity also to make it more efficient, more responsive, and we're extending the data sets that we are supporting in Aeroval. So new are, for instance, the ICOS surface data for methane and CO2. But also profile data is now being developed, the LiDARs of EarlyNet, and the ceilometers, and also satellite data are things that we're now developing. Another thing where we put much more focus is emphasis on case studies, and that's done in close collaboration with Mark Barrington from the weather room. So we go back to extreme cases in the past and reanalyze them, and so examples are shown here. So dust transport, big dust plumes are clearly a big target, and we had this special session yesterday about this. Volcanic eruptions are examples, also pollution events, but also clearly this North American fires is something that we are revisiting and looking at in more detail how CAMS was doing to describe these fires last year. And the last highlight I want to mention is, if I still have time, is the acquisition of new observations. So that was already mentioned also by Johannes. So we have these gaps in the data set. So we have America, we have Europe, we have China, but we hardly have any data from Africa and South America. And also in Asia, there's room for more data sets. So we are extending these data sets and also putting them into our quarterly workflow. And so, for instance, for Chile, we now have the Cinca data available, and we are using that also in our reports already. And we're extending to Hong Kong, to Taiwan, to Brazil. Also, the Japanese network is a thing we are considering and working on, and South Korea. Apart from that, we are also looking at aircraft and field campaign data sets, which is especially for the evaluation of the reanalysis, and also emerging remote sensing data products. So the new geostationary data from Tempo and GEMS is very exciting, and we also want to incorporate those data sets. Okay, that's my talk, so thanks for listening. And this is basically what I talked about to refresh your memory. Thank you.
Many thanks, Hank, for this nice presentation and also for setting up this stringent evaluation framework and with quite encouraging results. So are there some questions for Hank? Yes, please. Yes, it's you.
No, it's here.
Francesca. Oh, yes.
Thank you, Hank. So you show that you are validating the near real-time CAMS product. So every 3 months you have a new report taking into account the new CAMS versions, whatever happened during that period. I wondered, the reference data, does it also evolve, or do you use, for the past data, you use the same reference data because there's evolution there as well in all the different sources you use. So at every new report you always use the latest available reference data as well?
For the new reports, we really rely on this real-time data. So we have this cutoff time of 1 month. But especially for the reanalysis, we can use the reprocessed data. So we're not using near real-time data there, but also use reprocessed data sets when they are available.
So ground-based, the new ground-based data.
Yes.
Thank you. Yes, please, Guy.
Okay. Just a question. You do a re-evaluation and you find discrepancies, perhaps in certain cases. So what is the process to use the validation to improve the model? I mean, how is the result of these evaluations, which require a lot of work, useful for improving the model? What is the process?
Yeah, so Johannes already mentioned that as well. So apart from this, is really an a posteriori activity. So it's meant to document the quality of the data, especially for the users. But so we were really run behind the model development because the model development is already looking at cycle 49, especially cycle 50. They are already looking at, and of course we still work with cycle 48. So we always have that, we don't have that contribution in that sense to the model development. But clearly what comes out of our reports is looked at by the modeling teams, and if we highlight certain discrepancies, so for instance I showed a couple of things for the stratosphere, so those are clear leads on how the model can be improved, for instance for NO2 in the higher stratosphere. But the model development has its own tools also to look at how the model developments compare to independent observations. And one thing that we are discussing is how we can really share the tools more and more in the future so that we make use of the same data sets.
The fact that you do a posteriori is still a validation of the model.
Sure.
And potential problem with the model are seen and in fact sometimes are persistent over years. I think being corrected really is difficult.
Yeah.
But should there be a more established process to really take advantage of the validation and try to find why this is not working as well as it should? And maybe that's not in the program yet.
No, that's a good recommendation, and we can see if we can enhance that interaction with the modeling teams. Yes.
Thank you. Okay. Thank you very much, Hank. And now, CO2 MVS developments or preparations. So, Richard, please.
Yes, thank you, Laurence. Yes, there we are. So I'll talk a little bit more about CO2 MVS. I'm not going to go into a lot of detail, mostly because we also have a dedicated session in the afternoon looking at all the different projects supporting both the development of CO2 MVS and also CAMS more generally. So there will be more detail coming. So I'll give you a little bit of a high-level overview where we are with the developments of this important new part of the CAMS services that we are implementing in this second phase. My name is on there, but obviously this is a huge team effort with many people involved. You've all seen this slide and probably many times already, but I think it's still useful to really show the process of how we are working towards this new part of the CAMS services. For CAMS itself, we started with GEMS, Mach 1, Mach 2, Mach 3, really beefing up the science to get to the CAMS operational services. And we have a similar path line for the new CO2 MVS services. We started back in 2015, where there was a CO2 task force formed by the European Commission, thinking about, well, how are we going to design, how are we going to implement a Copernicus service that can support the Commission member states with the monitoring of emissions. And this was at the same time as the Paris Agreement. So clearly very important. So this task force continued. It's still there to provide guidance. But then in parallel, a whole range of Horizon 2020 and Horizon Europe projects started. And this has really been great that there was dedicated funding available from the European Commission to support development. And this slide, I mostly updated with new projects starting along the timeline, and you can see actually it increasing in terms of what is being worked on and how it can support the development of the operational systems. Right now we are actually at an important point on the timeline, which is noted by the operational ramp-up in CAMS. The COCO 2 project, which was one of the key projects in the development, finished in December. You will hear more about it in the afternoon. But it also means that now we really need to start implementing mature activities as part of CAMS in a pre-operational framework, if needed, operational where mature enough, but leading towards our goal 2026, where we need to be ready to take up satellite data from CO2M, the CO2 monitoring mission, which will measure CO2, methane, NO2, and have corrections for aerosol as well, but then also in parallel Sentinel-4 and 5. The other thing I want to point out, again, is that, yes, it's called CO2 MVS, but we're not focusing on CO2 only. Methane is clearly an important greenhouse gas as well, and we also want to use the same developments we use to look at other emissions, like NO2, like carbon monoxide. So it's really trying to build something that's flexible enough to deal with all these important problems. Yes. We're not starting from scratch. We actually already have various services within CAMS that are related to greenhouse gases. And again, I won't go into detail because there will be other presentations illustrating this as well. Starting with the inventory-based emission data sets we have on the global and the regional scale, European scale. Obviously, for all the air pollutants we need in our air quality forecasting, but also including CO2 and methane. And these are just two examples, CO2 on the left for the global, methane on the right for the European domain. So this has been an ongoing activity for many years already that we keep improving, also adding more detail both in spatial and temporal domains. But there will be more about this later. Then this slide was already shown by Johannes as well. We have our daily analyses and forecast of atmosphere concentrations of CO2 and methane at higher resolution than what we do for the air quality and the atmosphere composition in the global system. But it's a system that we have available that we also will use to support, for instance, the space agencies ESA and EUMETSAT with developing their retrievals for CO2M, for instance, or Sentinel-4 and Sentinel-5. But again, something that already exists and that we keep improving. And to show you that there's a lot of work going on to actually improve the IFS model, especially again in these supporting projects like J and Corso. I just want to show these simulations that we've produced within the COCO2 project of CO2, methane, and carbon monoxide, and I'll leave it to you to figure out which is which. But it really nicely shows how we, by further developing the model, introducing more of better emissions, better modeled emissions, we can really nicely represent what the satellite actually will observe. And you can see it's a very dynamic atmosphere if you look at 1 year, but this is actually what we see with observations. And this is what we then need to interpret to look at emissions, at fluxes, and using the different species to actually get information on the different processes. And especially between CO and CO2, you can really see the complementarity. These animations are actually available. We have published them on the website, so if you're interested to look at the full year, they are there to watch. Another thing that has been there already as part of the operational portfolio of CAMS, and again there will be more information about this later, are the atmospheric inversions of CO2, methane, and N2O, where we use in situ data as well as satellite data to look at net fluxes at the global domain. This has been relatively coarse resolution. There's work ongoing to increase the resolution and really take out the best out of the observations as we can. And this is already data that is being used by our user communities. A relatively new product that we have added is, and it was mentioned yesterday by Laurence as well, I think, is the collaboration we have with Carbon Monitor, and where we especially support the application to the EU countries, where we use activity data to provide emission estimates closer to real time than what is possible in the more detailed inventory work, where we have to wait, for instance, on national reported emissions, and there's a lot of work around it to really make good data sets. This is more on the fly, but trying to make use of information that is actually available to estimate emissions of CO2 in this case. And you can see here the behavior over time for the EU 27 and the United Kingdom, and also differences between years, and we separate this in some of the sectors as well. Very important is also that this is relatively new. We're trying to understand what we can do with it. And for instance, we have been comparing estimates from this system with the more detailed inventory-based data sets we have to see if it's consistent, if we really can get better improved emissions and also closer to real time. A very recent new activity is satellite-based monitoring of methane hotspots using Sentinel-5P TROP-OMI data. This is a new contract that we have with Esron, University of Bremen, and the Max Planck Institute for Meteorology, monitoring routinely the emissions from significant hotspots of methane emissions. Sentinel-5P has its limitations. There's a detection threshold, but it will identify the bigger emitters. And this is a new contract also really for us to see how can we use this data, and also with the interaction with our user engagement, how can we make sure we can provide some answers to the questions that are being raised. There we go. And the final existing activity is, of course, also the GFAS system, and there will be another presentation later today. Also an important component of the whole carbon budget, so we can already make use of this. GFAS delivers us emissions of many pollutants, but including CO2 and methane and related species. So again, something that already is there as part of the operational portfolio. However, we need to expand now in the coming years based on the outcomes of the research projects we've had. In the agreement we had for the second phase with the European Commission, we already identified the different areas where the portfolio needs to be extended. And I've tried to just illustrate here the different categories, and I'll go into a little bit more detail in the next slide. But it's basically looking at an integrated approach. We need to further develop all the different components that are part of this new service element. So there will be continued and even improved work on emission inventories of the greenhouse gases, in addition to what we already do for all the pollutants. Further development and the provision of global observation-based emissions and fluxes. So this work is mostly focused on expanding ECMWF's IFS system, so model development, but then also introducing new methodology for the data simulation to make use of the wealth of observations we will get in the future, especially from CO2M, to constrain emissions and natural fluxes. For the global system, it's also important to emphasize that, yes, the focus is on anthropogenic emissions, but we also want to monitor the natural component. How does the uptake of CO2 change with climate change, for instance? How do wetlands change related to methane? And this is something we can monitor with the global system as well. And then also use the same methodologies, the same approach for some of the other pollutants. The third component is the development and provision of hotspot observation-based emissions. So as I said, we have this first contract now in place, but there will be more to come. We were working, for instance, with ESA in the Copernicus Contributing Missions program to see if we can use some of the new upcoming small satellite missions that are often commercially available, but there is budget available within Copernicus to see how we can exploit this. So this will also something that will come. The focus at the moment is on methane, but of course we also want to extend this to CO2, and especially once CO2M is launched, we will have the data available to really look into this. The fourth component, very, very important, is, and I'll come back to that in a moment as well, is the co-design of specific user services. We need to deliver data, but we need to make sure that it's data that can be used with policy making, with different user communities at the European, national, and even local scale, that what we provide is useful. So we really try to work this out together with them. And then finally, we have budget to continue what we already have been providing as part of CAMS. Some of the examples I showed before to make sure we gradually improve the services we have. So into a little bit more detail, and the title of the slide is wrong, so don't pay attention to that. But I just wanted to say a few things about the ways we're thinking about it, and it's not completely out of the blue, but just to give you a little bit more detail. So as I said, we want to increase the efforts on the sort of bottom-up emission data based on the inventories we have, the activity-based emissions, what can we do more in terms of temporal profiles, in terms of spatial detail, in terms of emission modeling. All these activities are part of that, and that's something we greatly want to increase in the coming years. Second bullet here is what I already mentioned, further develop the IFS global modeling and especially also the data assimilation capabilities for greenhouse gases and their emissions. This is obviously very challenging. We need to be able to deal with enormous amount of data in a routine basis, day by day. So we're really trying to some extent redesign the IFS system to make that happen. But again, there will be more detail this afternoon, at least with some examples. Explore the use of satellite observations from the Copernicus contributing missions, which I just mentioned. We're really trying to collaborate with ESA to see how we can exploit this, exciting new data, but not straightforward to use, especially not in an operational system. Introduce CO2 hotspot detection based on available satellite observations. So far it's fairly limited, but there are new instruments being launched and coming up in the coming years, so we want to exploit this. User engagement, I already mentioned. I'll come back to that in my last slide. Very important then, develop and implement a good EQC strategy for emissions and service fluxes. Henk already talked about the global evaluation. There will be talk about regional evaluation, but we also want to put more emphasis on the evaluation of fluxes and emissions. And this is far from straightforward, so this is really something we need to develop as well. Yeah, and then continue the things we have been doing quite well already for many years, make sure we have continuous delivery of service. Just one slide to show the R&D through the Horizon 20 and Horizon Europe projects. This has really been great to have this funding available. We have had Che, Coca 2, now we have Corso and Katrine. There will be more in the afternoon about this. We also work together with quite a few other projects that are working on similar problems to really, as a community, evolve in this domain. But yeah, more later. And then I'll finish with this slide, because this is, of course, what it is about. We need to deliver data that is useful for the different user communities, different policy sectors, at European scale, at national scale, local scale. We want to contribute to global efforts like under UNEP with the Methane Observatory, WMO, the Global Greenhouse Gas Watch. All these elements are really key for us to contribute to. We've had discussions in Europe with DG ENER, with DG Klima, really trying to see how we can add value and how we can adapt our service to their needs. What are the questions they need to answer? What are the questions they're facing? That's important for us to know. At the national scale, same thing. We work together with several countries. How can we help them with their reporting obligations, for instance? How can we help them with monitoring the emissions and how they change? Well, you heard about the Global Methane Pledge yesterday, important, Paris Agreement, important, and then finally, also looking at local scale, how can we help cities, for instance? Cities are sometimes ahead of what countries do at national scale, trying to build greener cities, reduce their emissions. So can we provide data that help them to see if their changes have any impact? So very important to really work on this as part of the development, not leave it till we are operational, but really make it part of the overall ramp up. And with that, I finish and thank you.
Many thanks, Richard, for this nice overview of the preparatory work, but this is a lot of work for CO2 MVS. One question, one or two questions? More information will be given a bit later in the morning and in this afternoon, and so you will have the opportunity to ask questions. Many thanks again. Marion, yes, let's continue with the solar radiation service, and Marion, floor is yours for the introduction of the achievement of the year. Thank you.
Thank you very much. So, yeah, while I'm waiting for my slides, which are here, great, thanks to the team. Well, yesterday you heard me talking about more from the user perspective on the influence of dust on solar radiation. Now, let me focus a bit more on our main work here inside CAMS in a larger team, given here at DLR, but also at Vaisala Amin and at FNY, providing the solar radiation service as part of CAMS. So what did we do in the last year? This slide, those who are regular visitors, they know very well. This is my standard slide to start with. But for those who are first time here, just have this idea. We take clouds from the satellites, from the meteorological satellites, combined with all the aerosol information, water vapor and ozone we have here from the modeling part of CAMS. Couple that, put it into fast radiative transfer, and we get a time series. You can say latitude, longitude of your house, you click a button, you wait a few seconds, you get an on-the-fly processing with the most recent software version and input data, especially from the aerosols. We hear there's a lot of evolution over time. You get a time series. So what we did in the last year is we extended, that's the green box here, we extended to the Himawari field of view, so you can now go to Australia and part of Asia. And we also did a redundant processing chain at 2 institutions now, at DLR and at Vaisala. That, of course, is a lot of work in the background to ensure really very nice and stable operations here. Okay. This is also a new slide. It's an old information, but a new way of packaging that. And that's actually, we went to several solar energy conferences, and one colleague came back saying, Marion, on the one hand, we get a lot of feedback that you're so transparent, you're open with the quality, you're doing such a lot of information on quality control, you publish all that, that's wonderful. But the first-time users, they say, it's a bit overwhelming. We need a first to look at plot about the quality. And on the other hand, we don't have so many stations to look into versus ground observations. You see here in the full of the left-hand side, that's the full MSG field of view, 40 stations, and in the Himalaya we have managed to qualify 9 stations in the meanwhile. I mean, this is parts of Asia and Australia, 9 stations only. So we are always at the risk to exclude a station too early or too late. So making a mean bias is always a bit risky and not representative. So that's why we normally communicate all the stations we have to the users, and they say, look, if you're a Northern African user, you should look into those stations and not be kind of, take the information from other locations into account. We know that natural variability is high large. But how to put that into one plot at the end? Now we treat the natural variability, which is reflected in the different results at the different stations in the different geographical areas, now as a kind of an ensemble. Well, now we come up with a typical ensemble plot here, so that uncertainty you see is more natural variability than uncertainty, but that gives us a single plot to look into and also to monitor progress we do have. Yeah? You see biases, RMSE correlations versus that's relative values versus the mean of observations, and as said, both satellites field of views a bit separately because they have different characteristics we want to see. You see global, direct, and diffuse in the different colors, so all packed in one plot, and that's now our starting plot in the quarterly validation. Okay. The next news, we have a new product, and it's a derived product on the ADS system available. Remember, we have our primary product is a time series. It's an on-the-fly processing at the location of interest. But you may be interested in the solar radiation in the whole country or in a region for some system analysis study. And that ends up with users who want to have many, many time series. Yeah? So we offer them now, instead of getting again and again processed for everyone, that we have a pre-selected, pre-calculated gridded product. We decided ourselves we take an 0.1 degree spatial grid and a 15-minute temporal resolution. Yeah, we could have chosen different, but that's the way we chosen. We did the calculation ourselves for many, many time series and bundled them together into a new NetCADF file, and that gives now a gridded product in monthly file, which is on the ADS. So summarizing what I've said here on one slide, the primary product is the on-the-fly processing. So if you are in high-quality data interested into a local location, go always for the primary product. And there you can select from 1 minute, 50 minute, 1 hour, daily, monthly temporal resolution. And that's what the user community does. For example, if they go from the PV library, it's one of the interfaces they use to calculate the photovoltaic production at a certain site. That's connected, and that's where those users go to. If you're more into system analysis, large-scale assessment, you can take this derived gridded data set. As said, it's 2005 to 22 in MSG field of view. We're very close to release Himawari and extending that period to 23. So that will be regular update from time to time, and also solving bug fixes we might find. So we have this annual repetition of that, but we are always more than 1 year delayed, yeah, on this gridded data. Okay. Then we worked very heavily, actually started that 2 or 3 years ago, on which makes our life much easier. We have a large variety of different sources of ground observations, and we are handling them now all in a single thread server, in a single metadata structure, a single file structure, and do a lot of work of quality control and getting them into a single system. That's an example of an internationally now agreed on quality control scheme on ground observation data. And on the left-hand side, that's actually what is new. We have now about 10 different networks inside. Some of them are new in the scheme. There are more dots on here, and that will grow from year to year, is our expectation. We are also able to include campaign data that are not used in quarterly validation reports because they may last a year, but in all kind of development work, then it's now easier to handle them, and that's why part of these points come in. They're not operationally available, but they help us in development work. This is a link to Cameo, because the technology behind I've just shown allows us now also to handle lots of individual small stations from the network. Those are stations which operate global radiation observations only. Normally, we reject them due to that case, because all our quality control requires direct and global radiation measured at the same time. But on the other hand, it's a very nice, this is the French network, very nice coverage. So does it make sense to use them? Is that just too much data? Is it valuable data? Is it good enough data? This is the work we do in Cameo, but the infrastructure behind is actually the CAMS infrastructure. And yeah, we will see. We may come with that, but we are not sure. We see a lot of problems. So all those who are responsible for radiation networks and the Met services, there's work to do to make good data. Okay. So we are now CAMS version 4.6. That was last year, 4.5, the year before, 4. I told you last year we did a lot of changes in the cloud scheme, we did a lot of changes in the aerosols. Now the CAMS reanalysis was extended, and of course we're always adding on the aerosol part the most recent cycle, and we are regular monitoring that, and we see a next one to come, and we added the Himawari field of view. We did not change the clouds at the moment, and we did not change the handling of the aerosols so far. Okay, now let's a bit look into our assessments and ways to try to understand more about what we are doing. Because at the end, the users ask for the plot I've shown you. What is your bias? What is your RMSE? But in order to improve that, we want to understand more the details behind the scenery. And this is a way which proves to be very helpful for us, and we continue on that, is actually that we look into direct radiation from the surface observations, and you see inside the red boxes are different patterns, typical different patterns, and they're actually connected to different cloud types. So we have here an indirect radiation-based observation of the type of cloud. And this is a good tool to build groups in our results. And here you see it, so it's a bit busy. You see our different stations, so not too many, as I said, in this case, Europe and African stations. Then you see overall it's all biases, and then we have the cloud-free, the thin cirrus, aerosol-dominated cirrus, small cumulus, thin but not variable clouds, cumulus clouds, thick and broken, and overcast clouds. And then we have the different colors. And these are the different versions. So the most recent version is the red. And let's look just at that point here. That's the message I want to really communicate. That's the main for those kind of cloud type. We are getting better in the bias, we're getting lower biases. And if you look at the most of the stations, most of the classes, this is the main story that this one tells you. But there is still more. We still have this in the purely aerosol-dominated cases. The different regions behave different. If you look into that, like partly dust-dominated station, partly industrial, and so on. So this is at the end the monitoring of the quality of the aerosol model, and there's natural variability and also variability in the quality of it. Then we have typically negative biases here in the heterogeneous cloud conditions and positive biases here in the overcast cloud conditions. So there's obviously an issue with the cloud type or the cloud heterogeneity, which we should solve. On average, it's very nice. Users are happy that average is out. Yeah? But on the other hand, of course, we want to understand that better. This is the same plot, but for biases in direct radiation. Here the turning point is a bit earlier, yeah, with the cloud type, but it's the same story. And basically, we're improving version to version. This is nice, but there's still something to be solved. Okay, so the diagnosis tool is now ready. I can still not tell you what is the reason. Let's see. So, having this information, look, we are somehow, clouds is an issue. We can also say, well, there are other cloud products out. Why are you not choosing the SAF products, for example? Good question. At the end, the community doing those retrievals, which we use, and the SAFs, was the same scientific community many years ago. They were sitting together in the same workshops. They were having the same ideas. They're starting with the same stuff. But in detail, it's done different. And what we basically need is cloud masking and then the cloud optical thickness or optical depth. And so we have mainly the CAMS stuff, which in the most recent version is the merger with the nowcasting stuff. We started in our assessment with the nowcasting stuff as well, but now they merged actually both activities in the recent version, and that's why we look into the CAMS stuff Class 3 at the moment. And our main question is, would it be worth to take the other products and stop our own processing? And well, would it help us? So if we look a bit deeper, we managed now to have both the same basic calibration of the satellite instrument. That was a story in itself. But now we are not in that trap anymore of comparing really completely different stuff. Then we start with the same threshold-based probabilistic cloud masking, which is really old stuff. These references are the most recent ones, but if you go back in the, it's 1980s publications in the background. But then we have a big difference. We start, as soon as we have the slightest information on clouds, we take it as a cloud. While the cloud community would say, well, it should at least have 50% cloud probability to treat it as a cloud. And this is because we are so sensitive from the perspective of the solar energy. Yeah? We then have a more robust scheme for low optical thicknesses, while the standard two-channel approach. We have a different classification of clouds. Those cloud classifications are more dominated by the interest to detect hazardous cloud systems. Thunderstorms, hail, yeah. At the end, thunderstorm or non-waning thunderstorm, for us it's a dark cloud, we don't really care. What we want is the optical properties. We are much more interested in thin clouds. So we use just the dissemination of water and ice phase. Okay, so these are the differences, and if we apply both cloud mass and cloud optical thickness inside the radiation scheme we use in CAMS. So with all its maybe errors it may have, yeah, but is that what we have? Then all the blue bars are what we have operational in CAMS, and the orange ones are if we replace that part by the CAMS product. And here we see biases on the urban scale. The blue is always smaller. Rural scale. In the desert, it's a bit pros and cons. There we likely have more cirrus cases. This is cloudy cases only, so this points a bit towards the cirrus we should look into. For direct radiation, it's the same message. And if we go further, that's now the Wood mean square error. That's interesting because now it averages a bit out. So something is happening towards the RMSE. Likely that's a cloud mass versus cloud optical thickness. So we should look into where are the differences. If we look into direct radiation, it's still, what we're doing is quite good. The deserts are a special case. So this idea to just replace it and be better, sorry, that failed. Still, it gives us a lot of ideas where we can improve, but that's perhaps next year's story. Now talking about aerosols. This is a slide to remind you that our plan is not to be chased anymore by the aerosol team. They're coming up with new versions. Dust aging is changed or not. Then new emission database here and there. Oh, we have a new size distribution here and there. And that all changes the optical properties. And we, as solar energy community, for me, it does not really care if it's a dust particle or a very small particle which affects my breathing. And as an asthmatic person, I know very well what that means. But as a solar energy person, I say, well, I mean, at the end, I want to know the extinction. That's all. So I'm not interested in the types, but in the optical effect. So that means the very nice new step is we just believe you do the right composition, And at the end, you come up with optical properties from the overall mixture. And that's what we will take in future. And we will completely omit anything like, oh, if the CAMS team says it's this composition, it compares to the old opaque aerosol times as a factor times 0.4, whatever, and then we make an optical property out of it. Yeah? So we remove very old stuff by an overall modern scheme. Okay. So now we have coded that, we have tested that, and we are now in the operationalization, so the acceptance is somehow done. So we are kind of using the same aerosol input in a completely different way. First story is we should not make it worse by that, okay? So if everything is the same between version 3 and 4, we would be already happy. We see that there are a few more, that's biases, that's would mean square, clear sky cases, global radiation. We see there are lots of stations where the radiation is a bit better, a few are not. On average, it's not making harm and slightly doing better. So that's okay, we can then proceed and get a profit hopefully from all the evolution from the aerosol team. So we are going at the moment to have the lookup tables calculated and have the final acceptance test before implementation then. Okay, another activity we were asked to do, as we have this bunch of radiation data available, and the experience in how to quality control that, and it's a zoo of instruments, I can tell you, to look also into the forecasts. We have a radiation forecast inside CAMS. That's nothing we do in our contracts, but it's done by the whole CAMS team, of course. It's part of the modeling. And we have, on the other hand, the high-resolution model done by ESMWF as well. So this is a much higher resolve. This is 40 kilometers. The question is, how do they both perform? Are they meaningful? Is it meaningful to take the free and open data from CAMS? So this is biases, this is relative MIE, and it's relative RMSE. That's what really the users look at. If you want to be on the floor, to be discussed as a forecast provider, this you should provide, and this is what people look at. We split now into continental, desert, mountainous, polar stations, subpixel. So a subpixel means it's a station, for example, on the coastline, or on a very heterogeneous background. Yeah? So it's very difficult then to compare. And that's overall. So you see the green one, that comes. It's a bit worse. But what we expected to be here or something like that with the lower resolution. Yeah? It is not. It's quite good. It's on the same level. If we look on the direct radiation, same message. Yeah? It's not better, would be surprising, but it's also not too bad. So it's really an asset to look into, knowing it's open data. If you look into cloud-free cases, and now if you go more into the desert tick station, I've shown you yesterday a view graph, then we improved dramatically with the aerosols. Yeah, and I mean, coupling that, of course, would be a wish of the solar energy community. But that's another story as well. Okay, our next bits and pieces to come. I mentioned McClear version 4, so this change towards a new way of using the aerosol information, that the implementation is ongoing. We are experimenting a bit to replace the lookup table with neural networks, and if that is stable or not, let's see if we go that way or we stick with the lookup tables. MTG, the instrument calibration, some people may know here around, that's delayed. So we are also delayed a bit in that, but it's on the other hand ongoing, of course. Yeah, Cameo is doing quite nice, especially on scanning our aerospace with machine learning. So searching for the patterns which may explain the deviations I have told you. Make use of that. Yeah, gridded data for Himawari field of view is in preparation. That's the bits and pieces I will tell next year more in detail. And I think that's the final slide is just if you want to contact me after this meeting and our basics and documentation. I think that's it for today.
Thank you so much, Marion. Really impressive, the wealth of product that you presented. Any questions for Marion, please? Yes, Johannes.
Yeah, thank you, Marian, for a very interesting talk. I have a comment and a short question. So the general comment is, if you have ways to tell us whether our aerosol is good or not, we should really work on this to make sure this information is provided earlier during the cycle development. So this would be something very nice. I had a question on this comparison for the forecast days. So for the HRES ECMWF forecast, how do you, or where do you take the aerosol information from, or was this not shown in this plot? Was it only focusing on the cloud, quality of the cloud forecast? This was not quite clear to me.
Actually, in that sense, we are pure users. We go to Mars and download. And whatever aerosols are in, we don't care. We don't change it at all. We just take it as a customer, grab it and compare versus our ground radiation data. And then we do with another one, and that's the CAMS forecast. Again, grabbed from Mars, not changed. No?
The main difference is the use of prognostic.
Yeah.
Prognostic aerosols in the CAMS forecast, where the climatology is being used, and the resolution, of course.
And the resolution, of course, which then would affect the cloud scheme.
Yeah.
Yeah. And if I would be a commercial provider, then I would start combining the two. I would start correcting the HRES with the CAMS aerosols in the post-processing or whatever. Yeah. But it would be much nicer to have that done internally.
Yes, good job.
Well, you're saying that, I think we saw an example of that yesterday in the Belgium user session where they did combine the HRES with the CAMS. Yeah, I don't have the details, but...
Yeah, that's exactly. I mean, yeah, we can leave it to users as CAMS, so, yeah. But that's another decision, yeah.
Other questions? No, if not, thank you. Thank you so much, Marion. And I think it's time for the coffee break. So I suggest to keep the 20 minutes coffee break, even if we are a bit late.
Okay, hello. Welcome back from coffee break. Hope you're all energized for this session on regional services, policy tools, and regional evaluation and quality control. Yes? Hello?
It's the wrong one.
I'm asked to not touch it.
Oh, it's the wrong one.
Work.
Which?
How is it now? Is it good now? Okay. So you didn't miss much. I just wished you welcome back from the coffee break and hope that you're all ready for this session. So my name is Maria Bardal. I work at DG DEFIS in the Earth Observation Unit, and I'm the program officer for CAMS, which means that I follow up on all your work and developments in CAMS. And I'm the contact point for you to the Commission and the Commission to CAMS. In this session, we will hear about the CAMS regional services, the policy tools, and the regional evaluation and quality control. And we will start with the regional services and Gaëlle Collin from Météo France.
Well, good morning, everyone. So, well, is the microphone working? No. Okay. And is it better now? Yes, it seems. Okay, so I do need the presentation. Thank you very much. So yes, thank you, Maria. I am Gaëlle. Well, this is not my real voice. I'm sorry, my voice didn't really love the weather in Brussels, but I will do my best to give the upgrade without this, with this voice. So I'm leading the Regional Air Quality Project Service together with Augustin Colette from INERIS and with the support of Alice Desjean, our PMO, our Project Management Officer. And what I would really like to mention here is that we are giving this presentation on behalf of the whole CAMS 240 project team, which is actually, well, huge, big team. We are more than 40 people in this CAMS 240 projects. So let's start to get to now with the first slide. The first slide is just a short reminder of what CAMS 240, what this regional service really is. So, three important words: Europe-wide, operational quality service, which include 11 individual state-of-the-art operational model, as well as an ensemble that is calculated from these 11 air quality models. We actually have two kind of data productions. The first one, no, sorry, I just wanted to use the light. The first one is air, so the calculation of daily, what we call near real-time, daily forecast and analysis, and both for individual models and ensemble, and something that is new, and we already talked about it yesterday, Laurence presented it, the new optimized forecast at station. We will, of course, get back to it in the next slides. And here, so that is computed by Météo France for the near real time. And here, you've got the reanalysis that are computed, processed by Ineris. So as we discussed previously in the previous session, there are reanalysis, but not exactly the same way that the reanalysis are calculated for the global. Just a word on the reanalysis is that they are calculated on an annual basis. So we delivered since the last GA, we delivered the interim reanalysis 2023 and the validated reanalysis 2021, and we are currently working on producing the validated reanalysis for 2022 and the interim reanalysis for 2024. What is also really important to highlight is that, first of all, the regional service, sorry, I can't find my, never mind, is a routine service with a robustness. And that is really important because we've got users every day, and we've got this routine production, but we also have evolution of this service with the implementation of 2 upgrades per year. Also, last to highlight here in this introduction slide, the strong collaboration with the other CAMS services. We work really in a narrow relationship with, of course, CAMS 283 for the evaluation, CAMS 271 for the policy support, CAMS 261 for the input emission, and CAMS 221 for the observation acquisition, and of course also with ECMWF teams, the ADS teams, the Copernicus teams. So this is really a real link here with everyone. We have decided today to focus on 4 main achievements this year. So the first one is the upgrades we have performed this year. So here you've got the time, sorry. So here it is a timeline for the current contract regarding the different upgrades from the early 2022 to 2025. And here we are with this year two upgrades. The first one here, upgrade number 8, U8, in November 2023, was a major upgrade with the addition of 2 new species. The first one was addition of PM2.5 total organic matter and the addition of the PM10 sea salt dry. We also slightly modified the consistency of the pan and VOC output. Some refinements also for the production of pollen by some models. And we have taken into account updated emissions, the 2022 recent year emission provided by CAMS 261. And we also proceed with an intermediate upgrade last May, 2 weeks ago. This was a minor upgrade because it was just an optional upgrade to allow the willing models to upgrade their own production. So 4 regional models participated to this intermediate upgrade. So always very important, the annual upgrades. Then the other, the main topic this year, the implementation of the European air quality forecast optimized at observation sites. Well, it was not easy to find this name, actually, because it's quite long, but it means what it means. It is also called as, also known as CAMS MOS for Model Output Statistics, of course. So it's been operational since January. it is processed at the central regional production unit level. That means that it is produced from the ensemble output. And what is really important today is to highlight that this is a landmark, a real landmark. Yesterday, Hugo mentioned that, well, of course, AI is everywhere. And so what we'd like to say here is that this implementation, this operational implementation, marks the first step of operational CAMS air quality forecast based on state-of-the-art machine learning approaches. So it's really important, and we will see later in Michael's presentation that we've got the first results evaluated. So, well, this is a teasing for your presentation, and I would just like to recall that this method that we implemented is based on the results of the work that has been performed in Copernicus by Ineris in CAMS 63 project. So that's also important to underline. So now CAMS MOS is available for download in the Atmosphere data store for 4 species, so NO2, ozone, PM10 and PM25. Also important to highlight is that there is a dedicated common knowledge page that describes this product, and details article, communication were done for the users with tweet, announcement on the CAMS forum. And that is really important because, well, we have to help the users know how they should use this new product in addition to the regular CAMS ensemble. So this figure here is interesting. You already showed it yesterday, Laurence, but I'm just showing a little bit more in not green, because we don't have green, in black. In black, you've got the observation. Here, in blue, this is a figure that highlights the added value of CAMS for NO2 concentration on a specific period in January, for example. So in blue, you've got the ensemble raw forecast, and in red here, you've got the post-process concentration with most, and this has been averaged over all European stations. And so in this example, well, it's very clear that most can be very added value for users. Third focus is something on the short-term developments. 2 items here. The first one is the fact that we organized in last December a scientific webinar on observation with the participation, of course, of all the relevant team at the regional level, CAMS 221, 22, 83, with a very large participation, more than 70 attendees, and we had a lot of very interesting discussion, and that this meeting was followed up by a side meeting that was organized on Monday, this time together with the global models. And something we also wanted to underline today was the work that we are currently doing, preparing the operationalization of the weighted ensemble projects. So this project is was under development, and this is again an output of the CAMS 261 service produced by FMI. So this is a new method to calculate an ensemble based on some weights that we give to the different individual models according to the way they behave in the past days. So this will apply to 6 parameters. They are written here for all vertical level, and they will be calculated only for the forecast because they do need observation to be provided, and it will be an additional product to our portfolio. It won't replace the median ensemble that will remain our project, but it will be an additional product. And last focus for this presentation is on the long-term development part of what is done in CAMS 240 projects. So this is a work package a little bit different to think about long-term development. So it consisted in 3 tasks, and they are all completed actually. So the first one is a task on deposition that consisted in evaluating the deposition fluxes for key pollutants from all the CAMS regional model systems. Another task was satellite data assimilation. So with 2, I would say, outputs. First one, an updated version of the CAMS satellite operator toolbox, the CSO, and also the guidelines on how to assimilate Sentinel-5P NO2 observation. And last, the third task is the task on forecast initialization, which consisted in studying the impact of initialization forecast with analyses that were obtained from the assimilation of e-profile ceilometer and leaders with an application on one model. So that were our selection of the 4 main achievements this year. But, well, would like just to go with you to this slide, to talk, well, to think about the remaining challenges for the rest of, well, I mean, till the next GA on the end of our contract, actually. First of all is, well, we'd like to maintain, of course, the very robust production with 11 model. I may repeat it every year, sorry, but it is really important again, because you can imagine that it's not easy to produce every day with 11 model, to be able to cope with, I mean, some deadlines altogether. So that's really something really good, and so I would like here to thank all the individual models for their collaboration. Also, the next main work that we have to perform, the next milestone, is the preparation of the next upgrade Unite. So this upgrade basically will consist in the addition of 3 new species, the well, I mean, ammonium, nitrate, and sulfate. Of course, also an update of the emission, so the CAMS regional 2023 emissions, and also what is important here is that we will also comply with the new cycle, the new IFS CAMS global cycle. So usually we update during an intermediate upgrade, but here we're going to do everything at the same time. So this is something that is expected by October or November, if I understood correctly Johannes' presentation this morning. So we will be following the timeline given by IFS and CAMS Global. Okay, next bullet. This year, I've talked about this weighted ensemble project, so the idea now is to make it operational before the end of the year. And of course, to let the users know about how it works. Another topic is that we are going to secure the delivery deadlines of the reanalysis production, because we have a lot of users. First users is CAMS 271, so it's really important that the deadlines are secured. So this is, we are going to work on the monitoring again. We will also establish a framework to include the dynamic emission of residential PM. And last but not least, we will submit the system description paper. Yesterday, we celebrated the 10th anniversary for CAMS, but at the same time, well, our paper describing the regional service is now kind of old, and so we are working on a new paper to describe all the evolution and the actual state of the regional service. And since the contract is ending in April, we will wrap up the current CAMS 240 contract, of course. And so this was my last slide. Again, I would like to thank, on behalf of the CAMS 240 management team member, I would like to thank to all the CAMS 240 contributors. So here you've got the name, well, the name of all the 12 partners. And next year I will put some pictures of every people involved, but next year, so you've got time to give me a nice picture. And of course, thank you to the whole CAMS sphere, because we are really working together. So that's it. Thank you.
Okay, thank you, Gail, for that concise presentation. Any questions? Here's a question. Do we have a microphone? Yeah.
Just a question, kind of a general. Should it work? Yeah.
Yep.
So basically, you are doing an ensemble of 11 models, which gives you a certain dispersion of the result. But each of these models use, I guess, one single meteorology or meteorological evolution. Now, the meteorologists do a lot of realization for the weather forecast for the next days. Have you ever tried to look, if you take one single model and you take maybe 30 realization of the weather, how much of the dispersion you would have on the air pollution, on the air quality?
You mean adding an ensemble on the Met situation? Okay, well, that maybe our scientific manager is going to reply, yes.
Thank you. I don't know if can you hear me?
Yes.
Thank you for the question. So the quick answer is no. We have not tried to do that for the regional ensemble. But yes, we are doing it at the moment as part of the CAMEO project. So it's a research project, and there is a task there on uncertainty propagation in general. So we are assessing the uncertainty propagation in the models themselves, the regional systems themselves, the uncertainty of emission sources, and the uncertainty of the meteorological forecast. And actually, this is something which is done with the global model, the AFS model. So in that task, we expect to have quantitative information of the various reasons of this uncertainty, including the meteorology, but it will be from the global forecast aspect. But of course, we are looking very closely at that also for the regional ensemble, and depending on the conclusion, we might consider to evolve, but that's longer term.
All right. Okay, yep. And here we have a smooth transition between the presentations. So now for the policy tools, Augustin Colette from Ineris.
Thank you, Maria. Oops, okay. Thank you. So indeed, I will take a moment to brief you a little bit on the updates of the general production of the CAMS policy service. So just a reminder of the general objectives of the service. The scope of the work we do is really to provide a link between the wealth of expertise we're developing in CAMS, basically your expertise, everybody in this room, to air quality practitioners in Europe. Can it be at the European level, at the national level, or also to local stakeholders? Over the long term, we aim to ensure that there's a continued improvement both in the quality and in the relevance of the product for their use for policy users. So what we do more concretely is we develop this website, which we perceive as a one-stop shop for any policy users to be informed about what we do. It includes a number of online interactive tools, but also analysis reports that can serve as a long-term reference. We develop and conduct targeted studies, case studies that can last for 6 months, 1 year, 2 years, typically contributing to collaborative intercomparison exercise. We also take care of a sustained dialogue with the European national and local stakeholders, and at the European scale is typically various directorates from the commissions, but also EEA and GRC. And the last point, but not least, is a close collaboration with the Forum for Air Quality Modeling in Europe, which is FAIRMODE, and is really providing a forum for all modelers to discuss of the use of modeling application in the reporting under the directive, and I think that it's very important that CAMS has a very active role in that forum. So I will review now what are the main achievements this year and what's new, and I will start by starting to talk about something which is not new. Every year, more or less at this time of the year, I'm coming to announce that we are delivering the last air quality report for the previous year. And I'm very well aware that it's difficult to communicate every year something new which is not new. But anyway, I really wanted to start with this point because it's a very important product and we really want to advertise it properly. We believe that this document is really a showcase of the value of the CAMS products and the CAMS data in understanding air quality in Europe. It's a comprehensive report, about 100 pages, that has different aspects in the content. We describe the various air quality indicators that are of relevance for the stakeholders and how they change over time. We discuss how the last year, the 2023, was really specific compared to other years. And we also select a number of air quality episodes to really show how air quality is evolving in Europe and how the CAMS tools can help in this understanding. So what you will find in terms of highlight for this year, we have a focus to look at how the energy crisis that was starting in 22 might have impacted air quality in Europe in 2023. You're aware that the increase of the fuel price following the Russian aggression in Ukraine has induced a shift away from gas to other fuels. Some of these other fuels may be submitted to emit more air pollution, and typically that's the case if people move away from gas to wood burning. But at the same time, because of this increase in the fuel price, there's been a number of energy efficiency measures, sobriety, that might actually also bring a step closer towards the objective of the Fit for 55 strategy. So we conclude in this analysis that overall the impact in 2023 was relatively limited. There's been an impact in the winter 22-23, but over the rest of the year it was much more limited, and also because the price began to stabilize later in that year. Another highlight is the summer season. Last year's summer season was really special in Europe. It was much longer. We had really intense peak in June, and really something new, we had peaks in September. So that's something really that is some worthwhile to show, to bring forward. The ozone season was thought to be really concentrated on the most intense summer months, but it seems that with the climate we had last year, we had something much more favorable for a long summer season. And the last focus is on particulate matter air pollution. We had a very, very long episode affecting the whole of Europe for 3 weeks. Usually, typically, air pollution episode is about a week, and we had 3 weeks of various sources, and we insist in this report on the fact that indeed we have this dust and wildfires that make really the top of the media when it comes to use of CAMS to understand episode. You often see this contribution of dust or wildfires, but we really insist on the fact that we can identify the anthropogenic source very clearly in the regional products. So residential, agriculture, and traffic emissions are instrumental for this type of episode. So the form it takes, that episode, so you have this PDF report, and you also have a mapping library that we put on the website. It's an interactive view for the users to have direct access to the maps for their follow-up reference in the future. And the form of all this we bring forward in front of you, and we bring also forward for a number of other users as part of the communication and dissemination strategy. And I want to highlight this point because we are at the moment thinking if we should revise this communication strategy, and we need the input of the community for that. So what's happening at the moment is this interim assessment report is disseminated to policy users. It's designed for policy users to use that in their reporting under the Air Quality Directive. At the end, we have 27 users, full stop. That's relatively limited for the ambition we have for that report. So we are undertaking this reflection, how to increase the visibility and the uptake of this report. If you were here yesterday in the social event, the European State of the Climate Report was quoted quite a few times, and very legitimately for the visibility it has in the media. You may have noted that the interim assessment report on air quality in Europe was maybe not so visible, and this is something I think we should make an effort to improve that visibility. It can also go to scientific publication. Any ideas are welcome. So I insist on this in front of you because we need the relay of this community to make sure this report is used and disseminated, but we also need the input of you as a community to help us to identify ways to improve the dissemination of this product. In terms of achievements, I will go relatively quickly on the other topics because, again, some of it is business as usual. We don't publish only the interim assessment report. We also publish an annual assessment report. It dates a couple of years back, but it's more stable because it's not using interim up-to-date data. So this is really the long-lasting reference, and now it will stay on the website for a good reference. We also produce a number of other diagnostics, like looking at selected episodes, and we're publishing just now a detailed analysis of the very large dust event that occurred earlier in 2024. Besides this publication, we're also in charge of organizing events to put together this community of policy user workshop, and we are quite proud to have now a really robust community and really good turnover. We're talking about 150 participants. Last time it was about half and half physically. We were hosted by the French Ministry of Environment, which is also a very good sign of the visibility of the service and the interest of high-level stakeholders for what we do. And we also offer an online participation for people not able to join us. You may note that the two last policy user workshops were also in collaboration with Fairmode, and that's also very important for us to strengthen the relevance of the work we do for the use of the product in the policy process. An achievement of last year is to improve the guidance documentation that we provide on the website. We had a number of feedback in the past that it may be a bit confusing to understand the details of all the tools we provide. But indeed, some of these tools are complicated to explain. So we put together a very comprehensive source of all the information we could provide. And we have this long list of different types of information. First item was to take stock of Fairmode again and go to their guidance and their nomenclature to make sure we are aligned and using the right terminology. We totally revised the website. The entries are really different compared to what we did before. We are still experimenting with this view, and we have also other options to explore in the future. The web apps are more intuitive, and they have also included more dynamic information for the users who really want directly to play with the tools and not interesting to read the documentation. Even though we provide also very synthetic README sections, we have a frequently asked questions section which is quite long. Cookbook style of approaches for the user who wants to be guided step by step on how to use the tools. We also have YouTube videos. Of course, all of this is supported by some scientific literature to build the evidence, and we provide those references, as well as more up-to-date deliverables on the methodology, which as part of the CAMS activity, of course, we update every year. We also addressed a number of typical questions and case studies. We realize we have more than 30 case studies making use of these tools to analyze episodes that we produce over the year, and the user can look at that as well as training. What is still missing here is developing Jupyter notebooks type of approach to actually make some queries in the tool and have some personal use of the product, and it's typically something we're considering to develop, especially in the contribution we are designing now to this training organized by UMETSAT, ESA, and ECMWF in Oslo later this year. In terms of achievement, I want to focus on one of the tools. I don't have time to present all of them, but we develop a number of source apportionment products. Source apportionment product can be tagging the origin of the air pollution episode. For example, you're looking at air pollution in Paris, you want to know if there's a contribution from Belgium and Germany to a given day. That's the geographical origin of the source apportionment. But what's new is this year we started to do some sectoral source apportionment. So we're using this air control toolbox, which is a surrogate emulator of the Chimère model, to actually assess the contribution of activity sectors. We have now 5 main activity sectors because we recently added shipping, and we always had residential, agriculture, industry, and traffic. So that's including in the daily forecast, and in the example I provide on this slide, it's also available for yearly averages. So if you are interested in the climatology for a number of target cities in Europe, you will know what are the various sources. And that's for PM10 in that example, but also for other pollutants. Another point which is more technical is been working very hard to align the setup of the various models. We're using a diversity of source apportionment methodology. We believe they are complementary, so we're using tagging, sensitivity, emulator approaches, but we also use a diversity of CTM, and for the implementation of their CTM, we need to be as aligned as possible. So now we really use something which is more consistent, and we believe it's a strong added value in the reliability of the service. And also we increase the number of data available. You may note that several places of the website you can actually click and download the data, and that's also a long user request that we had. We're still developing new features that will come later this year, and specifically for the tagging of secondary organic aerosol, and also we're considering options for the tagging of ozone, which is difficult to communicate, but we're working on it. Last point is important. We're also considering providing all these source apportionment diagnostics at all European stations, not only these 70 cities we're targeting. And why we would do that is for the users, the policy users, to be able to actually use that in their reporting. You know, in their reporting, when they provide the data to EEA, they can also indicate when they have exceedances what are the main contributions, and if they believe that a plan targeting agriculture or traffic would be more efficient in mitigating these options. So the various countries have very different ways to do that, and they discuss within fair mode on the best way to do that. But we are in the position as CAMS to also provide this kind of European information for all at all European stations. And that would be a change of paradigm in the approach we always had in the policy service. Before, we were providing this as background information just for people to be aware of the source of air pollution. But here it could be something that would be directly used by the country in the reporting. So that can be really also a game changer for the appetite of the user in the data we provide. Now I move to user uptake, and I want to highlight again this activity on dust, but we had the opportunity to discuss that in depth yesterday. I put that in the user uptake because for us it's typically these member states that would use CAMS methodology in their reporting, and it's very important to develop such users. We're also developing other thematic studies, like I said before, and two of them that are quite important at the moment is the one on methane. We started to do some scenario modeling a couple of years ago, but we're still welcoming requests on the analysis of this scenario and how to bring up the topic of methane on ozone mitigation in Europe. And the last bullet is on source apportionment. We're just starting an intercomparison exercise in collaboration with Fairmode, and also a number of other research project. Something that's very important to ensure we have a good user uptake in the future is to adapt to the new ambient air quality directive. Of course, it was mentioned clearly yesterday. It's great that CAMS is explicitly mentioned in that directive, but now it's up to us to be on par with the expectations. I think it will bring further scrutiny to what we do, and we need to ensure we are relevant, we are high quality, and we develop the right quality control of the various policy products. Last item is important in the air quality directive. It's not only about the source apportionment and this type of things, but information to the general public is very important also for the directive. So that's something where we need to contribute. Moving quickly to the next slide, I want also to take a moment to speak about the next challenges. And I mentioned briefly this issue of quality control. We're doing all this source apportionment. It's very difficult to assess source apportionment. Nevertheless, there are some information that are available from field studies, from some type of monitoring, and it's really not trivial to compare to what we do, but we need to do all our efforts to actually perform and try to use this data. And it's actually the scope of two projects at the moment, ERA Urban and Cameo, where similar works are being done for different products. I just wanted to highlight what we've been doing in ERA Urban for the evaluation of elemental carbon. So we have a number of monitoring devices running in Europe. They don't measure elemental carbon, they measure black carbon, which can be translated in terms of equivalent black carbon. And from this apparatus, you can also derive information on the fraction coming from either liquid fuel or solid fuel. There are large uncertainties in the way this is actually measured in the field, but we need to actually use this data, and we developed this demonstrator to actually compare on this plot here the relative fraction coming either from solid fuel and liquid fuel in the modeling, so the regular CAMS 40 production, and in the data that we can get in collaboration with the actress colleague. So this is a really important work at the moment, and we believe that within a couple of years we should be able to do that on a more regular basis. Second point is on the visibility of the service. So like I said, we're working hard to revise the website, ensure it's good. We're considering revising the communication strategy. We also need your input to check what we could do to be more attractive and so on. But there's also 2 points I want to highlight. If we want to meet the expectations of policy users, they're really always asking for 2 things: exceedances and high resolution. So they want our products to be able to detect the peaks, and that's why all the development with the model output statistics are really welcome. And they really also want to have higher resolution. That's why we're working hard, also in collaboration with the National Collaboration Program, to make sure that the background information we provide can be used for further nesting. And this is, we know there are huge expectations, we know there are very rapid development, and we have to keep an eye on this. Last point, which I wanted to provide to give a bit of further perspective, it's a bit beyond, maybe 5 years, but it's oxidative potential modeling. In the new directive, there is this topic which is mentioned, and there is a lot of interest into providing some type of indicators that are translating something about the toxic impact of PM. And it could be, for example, OP, but there are other metrics. And so that's why in this project Terra Urban, we are developing the modeling of OP, collaboration, very close collaboration to people doing the sampling in the field. It largely relies on the source apportionment methodology. That's why it's very relevant also for this policy service. Everything we are doing on source apportionment is required steps to move towards OP modeling. But then we also combine with this measurement, and what we will be able to provide over the long term, and we already have some demonstrators, there are maps of OP, map of the toxic power of PM. Here it's the scale of Europe, but we could also provide the long-term trends that's provided by the colleague from Met Norway, or even a day-to-day forecast of the total OP in PM and the relative contribution of the various activity sectors. And that's the example, of course, provided by TNO with the Lotos Euros model. So that's just starting. I want to highlight there are still some development. There are a lot of work in the harmonization of OP measurement, also for the source apportionment. But I think it's a very promising prospect, and I'm sure there will be a lot of appetite for policy users in this type of products. With that, that's finished. Thank you.
Thank you. Very well explained. So are there any questions or maybe comments, suggestions for how to make the report more visible? There's one here.
Thank you, Augustin, and also Gail for the previous presentation. So my question is a little bit a combination of both, but I know you are up to your neck in both, so that will be fine. So Gail showed this result of the machine learning approach to improve the prediction and forecast. And you also say here that this is what users really want, good exceedances exactly at the observations. But I noticed in the graph from Gail that the difference in that plot, at least, was like 30%. So 30% higher with the machine learning added. So that's quite a lot. And at the same time, in the policy, you have mitigation strategies that show a toolbox where you can see that if you reduce this emission, you get this kind of change. But with the machine learning approach, you don't know which sources are responsible, right? So I'm just asking maybe a bit of a philosophical question. Will your mitigation advices still match with what you have in this machine learning prediction?
Okay, it's an excellent question. Of course, I could answer in different ways and speak for half an hour on the topic. Maybe the most important thing to highlight is in the machine learning, we have CTMs. Actually, the regional modeling is one of the predictors and is one of the most important predictors. And if the CTM copes with the bias it usually has, then the added value of the machine learning is reduced. So we have an interest to keep developing CTMs and to be as good as possible with the CTM. Because if we are too far away, indeed, we are left with this missing mass that we compensate in some ways, and we cannot track back to activity sectors, and we cannot relate to the mitigation measures. So I think that we have to engage very actively into AI and machine learning and so on. That's a no-brainer, but it doesn't mean that we have to stop all the efforts we're doing in the CTM modeling, because if we want to have some causality, some inferential impact on the policy measures, the CTMs are still the key. But otherwise, there are a lot of approach and a lot of very active literature in this issue of propagation of the bias in the scenario modeling, so we can discuss that further. But the main message is really, it's not because we're talking about MOS that we're not talking about CTM anymore.
All right, thank you. Again. And now, to finish this session with the already very much advertised presentation on regional evaluation and quality control. Please welcome Mikael Gauss from Met Norway, or Meteorologisk Institute.
Thank you. And I also would like to acknowledge the entire CAMS 283 team, regional evaluation, because they're doing most of the work, obviously. I'm only presenting it. So what are we doing? We evaluate the products from CAMS 240, regional production. So that is the daily forecast and analysis, and it's the annual interim reanalysis and validated reanalysis. And we disseminate our evaluation results both on the web, daily updated, and in reports on a quarterly and annual basis. If you want to have a look, maybe not right now, everybody at the same time, but later when you have time, all the evaluation results are publicly available. We are honest about everything. You can see updated results every day, or you can download the PDF reports and have even a closer look. The measurements we are using, it's all kinds of measurements. It's in situ data we get from the countries via EEA and CAMS 222 and Météo France. There are sonde measurements from meteorological stations, aircraft measurements from IAGOS, satellite measurements, mainly TROPOMI right now, Sentinel-5P. If there are any observation providers in the audience or online and you don't see your logo, but you know that they are contributing to this, please let me know. I'm of course happy to add all the logos I need to. We are aware that there are hundreds and thousands of people behind those measurements, and of course without those measurements we would not be able to evaluate these models. Main achievements in 2023-24, I would like to mention all the web graphs and EQC reports I have already mentioned. They are delivered on time, so that's an achievement. But what is new since last year is the evaluation of the now famous MOS dataset. I still call it MOS, although the official name is much longer. Then we have included a new experiment which is called Current Season, where you can see results for the ongoing season. Right now that would be the summer season that started on 1st of June, but we go at least 30 days back in time. That was the user request. And then a major breakthrough was the evaluation of pollen. We did that for 2022 and published it in January, and now we are eagerly waiting for 2023. And yeah, we will have a contract with EAN to get the measurements pretty soon. EAN would be the European Aero Allergen Network, which provides us kindly with pollen measurements. And then there were several refinements for the above surface evaluation. For example, the global model is now included in the aircraft measurement comparison. So, and there are a few things like that that have been done this year, very recently. So this is how the CAMS Regional Evaluation Server looks right now. I already mentioned the new experiments. It's current season for the forecast and the analysis, and the MOS evaluation. So again, if you go to that website and click and play, you will see the performance of each of the 11 regional CAMS models and the ensemble for whatever statistical parameter you're interested in. And this, now I have to focus a little bit because I could overwhelm you with thousands of plots and speak for the rest of the day, but we decided to focus on MOS, this machine learning optimized dataset at a selected number of stations. And in the left column you see the ensemble performance, and on the right column the MOS performance. In the upper half, that's the tempo-spatial correlation. That should be as close as possible to 1, and in the lower half the bias. And probably you have read all the numbers already, so you see that the MOS dataset greatly outperforms the ensemble. And that is for the first day of the forecast, I have to add. No Michael Gauss presentation without a fair mode plot anymore. So this is a fair mode plot, and I spent lots of time on explaining these plots last year. Today I will only repeat that the goal here is to be within the circle for each of the stations, at least 90% of the stations. And you see the MOS dataset here in red. does this much more easily than the ensemble. And so that's a performance gain. And usually I don't overload my slides with plots, but we made an exception here. So you see here in dark blue it's MOS, and light blue is the ensemble. And this is ozone root mean square error, which should be as small as possible. And indeed, MOS is consistently smaller than, has a smaller RMSE than the ensemble. And this is another example, fractional gross error for PM10, should be as small as possible. Again, MOS is clearly below. That means better than the ensemble. And this is the bias, should be as close to 0. And you see the dark blue line, which is MOS, is much closer to 0 than the ensemble. So that's good. And then correlation should be as close to 1 as possible. Here, the dark blue line is much higher than the blue line, so that's also good. This is good. So this is the bias as a function of forecast hour. Bias is smaller in MOS than in the ensemble. That's good. Good, 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 and so on. But there's one exception, and that is the temporal correlation as function of forecast hour. It's fine in the first day of the forecast, but in the second, third, and fourth day, you see that the blue line has a lower correlation, temporal correlation, than the light line, the light blue line, which is the ensemble. And this is, I should have written being investigated, because the producers of the MOS data set are on it, and I'm confident they will find the solution pretty soon and update this product. And then today's special, ECMWF asked me to say a few words on the interim reanalysis and validated reanalysis. Most of you are very familiar with these products. The validated reanalysis assimilates data that are quality assured according to the criteria set out in the Air Quality Directive, and they are usually done almost 2 years later, obviously with newer, more updated model versions. But you have to wait for them. So there are two important questions. Is the RA that comes fast, is it reliable for your, is it usable for your purpose? And then how much better is the VRA? Is it worth waiting for? And the short answer to the first question is yes, and I will show you that in the next slide. And to the second question, it depends a little bit on what you're using these VRA assessments for. So if you are a policymaker, then I think you're even obliged to base your decisions on validated data. So for that, you simply have to wait for VRA. And I will show you that VRA is indeed a little bit better than the IRA. So that was my promise, and this is how I keep it. This is a plot made by Ineris. And the green bars are VRA, and the orange bars are IRA. Left, RMSE. Middle, the bias, and right, its correlation. I selected NO2. You would see about the same results for PM and ozone. You see that VRA is always a little bit better than IRA. And I have to add, this evaluation has been made against exactly the same set of data, which does not include the stations that have been assimilated, obviously. But there's one caveat in this comparison. It's that IRA 2021 was done with 8 models and VRA with 11 models. So I think probably the difference between the two would be even smaller if you redid the IRA with 11 models. But again, VRA is a little bit better, but you have to wait for it longer. And yeah, I'm a modeler, and modelers usually say it's performing well, it's satisfactory, and by and large, and so on. So Fairmode has provided us with an objective method of evaluating models and telling if they are fit for purpose or not. And as I said a few minutes ago, the goal is always to be within the circle, and even the IRA is within the circle, so it's fit for purpose. You can use it. It's a reliable product, and it's fast. But the VRA is just a little bit better. Okay, and then remaining challenges and next steps. The documentation, I'm getting a lot of questions from users all the time, so that means that the documentation is not optimal, and I'm in the process of revising it, making it better, so I get less questions. It's based on the frequently asked questions I'm getting, and we will publish that during the summertime. And then up-to-date measurements for pollen, I already mentioned it. The contract is just around the corner with EAN. Improve consistency between models and measurements. We had a session earlier this week about that. It's, for example, about wet PM versus dry PM, what is measured, what is modeled. There's a lot of things to discuss about that, and still some things to improve, although we have been doing this evaluation for so many years. Then fair mode, for those of you looking at fair mode plots on the web, they're still not completely compliant with what fair mode proposed, but in the quarterly and annual reports, it's completely consistent with what fair mode has proposed. So, and then respond to user requests, we are doing that all the time, but there's still some requirements in the pipeline. And then I would like to add more pollutants. For example, dust is now operational output from CAMS 240, and there's a lot of interest. We have heard that many times this week. And we should not only evaluate the models against PM10 measurements, but also against dust measurements. There are not many of those, but there are a few out there, so we should be using them. Above surface evaluation should make it into the website. It's still only in the PDF reports. And then the users should maybe enabled to make their customized reports. So you select what exactly you're interested in, you push a button, and you get a focused PDF report for your personal needs. So that is something I would like to implement. That's all from my side for today. Thank you very much.
Thank you, Mikael. Any questions? No? Always one question.
Just a question. Can you show that the you can recently show that VRA is better than IRA. So there are at least 3 reasons for that, I could imagine. So one is that there is more data coming for VRA. Second is the data are quality assured. And the third one, there is almost 2 years of model state evolution, model quality evolution between them. So how would you rank this 3? Thank you.
I don't know. My guess as a modeler is that model development is the most important reason. That we haven't. It would need a special study for that. I don't know. But really, my gut feeling is model development. No joking.
Okay, thank you, and thanks to all the presenters from this session. We will move directly to the next session on emissions, and give the floor to Richard.
Yes, so we move on to the important topic of emissions, and not with a future look, as we've discussed before, but what are we actually providing now as input to the models, but also as supplementary products within the portfolio. We have a slight change in the program. Philippe CS apologizes for not being able to be here in the end, but we have an additional short presentation on GFAS as well from Johannes Kaiser. But we're starting with Hugo Denier van der Gon, talking about global and regional emissions.
Yes, thank you very much. I'll do the regular thing. Yeah, microphone is working. So, thank you very much. My name is Hugo Denier van der Gon from TNO, the Netherlands, and I'm coordinating the CAMS 261 project on global and regional emissions. And of course, we do that in a really good European style. So we have 8 countries represented, 9 institutes, and really from north to south and from east to west. So I'm really very happy with this team. Let me move on. So the annual process and emission updates in the project.
we actually have, like, let's say, 4 core parts. So we have anthropogenic regional emissions that are used in the CAMS 240, that was presented before. We have anthropogenic global, that's used in the, for example, CAMS 235, that was also presented this morning. We have biogenic, well, I should say natural emission data sets, and that includes biogenic VOCs, volcanic SO2 emissions, soil NOx, and ocean emissions, and we have shipping emissions. That's not all we do, but these are that we provide annually, and then of course we learn every year and we try to improve in the next year. The other important things that are really coming into these different data products are that we add emission characteristics, and most notably the CAMS tempo data sets, both for regional and global, that are being made by Marc Guevara from Barcelona. And we look at special cases, for example, when there was the COVID pandemic, or when we saw issues surrounding PM in the emission inventories. There's also, which I think is very useful, and I'll show some of that, at least 4 times and sometimes more, a direct interaction with either the regional production or with the global production to discuss issues that are being seen in the use of the emissions in these models and the feedback we get. And of course we document and publish the results. These two, unlike some of these other projects, these components are quite independent, and that's not so difficult to fathom. If you're making a biogenic VOC emission, you don't have to interact very closely with the people making a shipping emission inventory. So these are really all kinds of pieces in a puzzle, and it only really comes together once it's used in the models. So that's also why this interaction with the modelers is so important. It's the only way we can learn from how everything is actually working together, because we have anthropogenic VOCs, we have biogenic VOCs, but there's not a way to compare that other than looking into the outcome of the models. So I will be jumping from one topic to another. That's a little bit tiring. On the other hand, the advantage is if you fall asleep and you wake up again, you're probably right at the start of a new topic. So then it doesn't really hamper you that you missed the previous ones. I start with the regional emissions. This year we prepared the CAMS Reg version 7 that is based on the data reported last year, and so the CAMS Reg, the latest year in CAMS Reg version 7 is 2021. Why do we make these new versions every day? Every day, I wish it was that fast, every year. Because these updates that the countries do in their reported data remain very important. And in this slide you see 2 countries, Poland and France, as just an example, and you see the PM2.5 emissions for the same year. So all these 3 bars are all the emissions in 2018, but in the version 5, the version 6, and now the most recent version 7. So you can see the changes can be quite big. And I show here PM, but I could also show this for some other components as well. So it's really important that we do these updates, and then this most recent version is also used to make the recent year estimates for 2022 and 2023 that now flow into the CAMS 240, and that's really something that was an achievement of last year. Also, and that connects a little bit to this graph with the different bars and the changes that you see here in the PM data from these countries. I think due to CAMS and surrounding projects, the issue of that there is condensable PM, that should be included in the particulate matter modeling, is now so widely accepted there are actually only a few countries who don't do this, and it is no longer worth it for us to have 2 separate data sets. So we only provide 1 data set now that is, in a few cases, gap-filled with condensable PM. We also have a little bit of room to sometimes look at things where we think we could still improve. And the last year, the General Assembly, there was this national collaboration program. Norway pointed out that they were going to rethink their particulate matter emissions from road wear, and that's a special case in the Nordic countries due to the road sanding and the use of studded tires. So that also made us scratch our head and look into it a little bit more. And what you see in the bar chart on the right is in orange you see the results from a bottom-up model that's being developed in the IRI Urbans project that does not really take into account these winter conditions. And you see in pink the results from the new inventory. And the blue arrows highlight Finland and Sweden, where you can see that there's a very large additional flux of PM from this road wear. And Norway flagged that, and we're going to look into it. So they are going to change their emissions, and so in the next version, CAMS version 8, Norway will be in that way similar probably to Finland and Sweden, but maybe the most important thing is that this emission is also happening at a certain time. It's not year-round. It happens when the snow and the ice melt and this pool becomes available, and in collaboration with Norway and most notably Bruce Denby, we were able to also make a specific temporal profile for that. So this will really, this is of course only true for the Nordic countries, but it's a nice new thing that we will bring into our data set. Now jumping to the global emissions, one of the achievements is that we have a publication out that describes version 5.2. It's important that we have good data or papers to refer to when you use it in the models. And of course in that year, again, this annual cycle, version 6.2 of CAMS Club Ant was released. And one really relevant change is that we also changed the partner. So now Max Planck Institute for Metrology is responsible for the further development of the CAMS Club Ant emissions. And they are at the moment putting their teeth into the first task, which is the extension to the year 2025, which is almost ready. This is already a picture from it, but there are some final checks and things being done. But this will be delivered on time, and that means that now this process of change of partner has also been completed, and I'm really very happy about that. Moving to the natural emissions, so as I said, really jumping topics. This is the work from Katerina Cinderalova and Charles University in Czech Republic, and the main achievements are, of course, the addition of an extra year, and I immediately point you towards the bottom graph, where you see this red bar. So the isoprene emissions for the year 2023, they surpass any of the previous years, and that's maybe not a result, not very strange, because 2023 was the warmest year on record. So yeah, these isoprene emissions from forests are very temperature sensitive, and you really see that. But you also see, I think, if you look at the sequence since 2000, there's really an increase in these emissions. And that will be important. One other thing that they really worked on is, together with CAMS 235, is to support the development of an emission module in the IFS to predict these biogenic VOC emissions. And these are plots shared by Vincent Huinen from CAMS 235, where on the left-hand side you see the result from the IFS online model, and to the right you see our CAMS GLOB data set. If you look from far away, the patterns look quite similar. If you zoom in into details and, for example, look at Europe, you can still see quite a significant difference. But that it's working, I think, is a major achievement of this year, and that there is still some work to do for the next years. That's only good for us. Another aspect of the natural emissions are the soil nitrous oxide emissions. This is work done by Dave Simpson at Met Norway. He extended it with a an extra year, so that's available. And at the moment, there are comparisons being made with these when you use this in the model and you compare it to tropomi observations. Also, he's testing different estimates, so also making a new version. So here in these plots, you see in the colors, you can see the CAMS version 2.4, that's in blue. Very important, in black are the observations, so that's where you want to be at least as close as possible. And then you see in red, also important if you don't include that at all, and there is very clearly that you underestimate compared to the observations. So adding the soil NO as first is already quite an improvement. Then you can also compare with the yellow bar, which is from the SEEDS project, DEXO satellite based. But I also heard this morning that there is some error in there, so I think we should maybe wait with that comparison in more detail. But anyway, these are ongoing investigations, and it's really making really progress in each year. When I see these plots, it looks better and better. So happy with that. Another, the last natural emissions part, well, that's not true actually, but it's on the ocean emissions by one of the previous speakers, so Michael Gauss doing this. He extended the data set with 1 year, but I think I would like to stress especially the development by very cleverly working together with other teams, in this case the Norwegian Earth System model, and created a new data set. So on the left-hand side you see the current one, but you now see on the right what will be after the implementation of this new method. And most notably, some of the artifacts that we see in the before picture, where you can, for example, recognize a ship track or so, these are much more smoother in the new data set. So it really looks more consistent and more advanced. So I think that's also a nice piece of work. Then the shipping emissions are an important component in our project. We provide global ship emissions, regional emissions, but also emissions for the European Maritime Safety Agency. So that's a very nice collaboration, again, also for CAMS, I think, with EMSA. This work is done by FMI in Finland. And they have prepared a new data set, so the 2023 emissions data. They're not yet available for CAMS with all the pollutants, but the CO2 for EMSA is already, and you see that map here. One of the insights over the past 2 years is really that they now model all these ambient conditions in their emission model, so wind, sea ice, whether the ships are going against the current or with the current, and that has a large impact, and a large, I think, easily 10% additional emissions when you do not include that. So, and that's quite a lot on CO2. That's a lot. The other natural component that we have is done by Chalmers University, extending data sets for sulfur dioxide, degassing for the volcanoes, but also very close interacting with mostly Mark Perriton for the CAMS Weather Room. And this is from a press release by CAMS, where the plume from one of the recent volcano outbursts on Iceland is modeled, but and so that's the model result, but the flux was constrained with the ground-based measurements that were also collected through the collaboration that Santiago has from Chalmers University. So this is, I think, also a very nice way of how data from the CAMS 261 project flows to feed, well, things like the CAMS Weather Room. Finally, we have also a work package led by Mark Guevara on the support of the CAMS production systems, and I want to highlight one aspect of that. I think this interaction is really important. It's indeed intended to support the implementation and testing of emission data sets. And what you see here are, on the left-hand side, figures model results for 2003 on top and 2019 at the bottom. The dots give and the color in the dots give the observation. So for wet sulfur deposition. And basically the story is that for 2003 those results are quite nice, but in 2019 the model has a large overestimation. And then we also started to look into, so why is this possibly related to the emissions? And in orange you see the CAMS Club ANT emissions, and in blue you see the US EPA sulfur emissions from especially the power sector. And you can see that in 2003 these actually match very nicely, but there is a growing gap over time. And in collaboration now with CAMS 235, we decided, can we use this information to maybe scale the input to the model? And this morning over coffee, Samuel Remy already told me that the first results of this test look very promising. So, and this is something we need to think about more in the whole process of the emissions data set. How can we use this kind of information? But first, get feedback from the models. Does it work? Does it help? And if so, yeah, it's really worth time spent. Then we document our data sets. I've sent you messages from volcanic emissions, shipping emissions, but if you want to know more about it, I suggest you go to the documentation of the CAMS emission inventory products, and there you will find all the different versions, but also the contact persons, and so that's, I think, a very nice resource. Of course, we also publish data, and this is just one example on the lessons learned from these multiple near real-time estimates during the COVID pandemic. And so that's... And I come to my last slide, the remaining challenges and next steps. So one obvious challenge is that the contract will end next year, and that might disrupt the production cycle, so we need to think about that. It's also an opportunity because we can think about new items. And some of these would be, and those are, I think, challenges for us. How do we integrate data or insights or new models or whatever that come out of the CAMS evolution projects and also some other projects. So that's true for Cameo and seeds, but also for the greenhouse gases, where we now at Che, Coco2, Corso in preparation for the CO2 MVS that Richard explained. That means maybe more emphasis on the greenhouse gases. That was actually already announced this morning, but for us that would also be relevant. So what should we focus on and what should we include? Emission uncertainties. We made a report last year about the kind of uncertainties that are associated with these different products. It's getting more and more important, but it's a considerable task. So this is also something to think about if we need to include that. It's not a simple add-on. I usually say I prefer to make an emission inventory than to provide the uncertainty of the emission inventory. It's just a lot more work. And very relevant, how to use satellite-based emission estimates in CAMS 261. We use it already for learning from discrepancies or testing some case validations like the soil NO and Tropomi. But when you really want to integrate it into your emission inventories, you run into conflicts that there is no sector detail in the satellite data, there are no country totals. So we need to think about that, but because it is obviously the way forward. And with that, I'd like to end and just show you that these CAMS 261 meetings are never fun, they're just hardworking.
Thank you, Lupo, for this nice presentation. And I just want to pick up on your last point, because this is actually a really nice way also to prepare ourselves to interface with member states, with the Commission. How do we translate the observation-based estimates into what they actually need to do? So yeah, having this capability within CAMS itself already to look into this problem, we should exploit that. We have time for a quick question. Guy?
Yeah, just a quick question. The first one is that everything seems to indicate that the EDGAR emission that we're using very much as the basis seems to diverge very much from many other inventories. And so that is a major issue, I think, for CAMS in the future. Maybe we should go away to a certain extent from EDGAR unless, we see some improvement there. Second point is this, you talked about the the heat waves and how the heat waves change, for example, the emission of biogenic species like isoprene. But a study that we did in Asia showed that when there was a heat wave, anthropogenic emissions were changing dramatically also because of the higher request for energy, for electricity, air conditioning, and so on. And so I'm kind of thinking that in the future we'll have to put some kind of temperature variability on some of the anthropogenic emission in case of heat waves occurring. So that's kind of something we should be thinking about.
Okay, so 2 questions. The first one on the EDGAR database. Yes, I agree, but I think also, and I also don't agree. I mean, it's really difficult. We need a stable data set to build up on this CAMS Club ANT, because you also have to see that if we would have to replace that, you would need a team of 5 or 6 people working on that continuously, and we simply don't have those resources. So we have to be pragmatic. Then again, I think one of the things that we saw with this slide for the US, for example, and that is also one of the challenges that we should try to solve. How can we make more use of this regional information that's also becoming better and more regularly available? And should we infuse the EDGAR data set with that? And another thing, which is also, I think, in my mind anyway, but we also had these CAMS projects, for example, on Carbon Monitor. They provide CO2 data up to near real time. So maybe we can also start to. So I think we still need a robust basis, but we need to be more flexible in how can we make that more better towards the current time, because that's where we see the deviations. And on the heat waves, and yeah, I mean, I want to be short because I don't think we have the time for it, but it's interesting because things will change, right? I mean, it's not only the heat waves, it's also warmer winters. So there are changes everywhere, and how these changes influence are very cultural, very different. If you do all that air conditioning with your solar energy, then you don't see so much change maybe in the emissions. If you do that using coal-fired power plants, you have a different thing. So. Yeah, interesting topic, but I can't, and we need to think about it. Things will change. They are changing. Yeah, you see that.
All right. Thank you very much again. I will move on in the interest of time. It's always a pleasure to invite Frédéric Chevalier to the podium. He will talk about the atmospheric inversions of the greenhouse gases.
Thank you very much, Richard. It's an honor and a pleasure to be here once again at the CAMS General Assembly after all these years. Last year we were 4 partners, CA, LSE, my institute, then NILU, TNO and Amsterdam University. We were called CAMS 255. We are back this year with a new name, CAMS 255 BIS, and we have 2 additional partners, science partners and KNMI. Some of the people are in the room here among the partners. I will explain a bit later why we needed these 2 additional partners. So I think that's this one. So we are back, stronger. We are back with the same products, even though we think that they are better. I will also explain in a minute why it's the case. Our products are CO2, CH4 and N2O fields for concentrations, 3D concentrations and 2D fluxes. You have an example here with a field of CO2 at quite high resolution. We have reached 1 degree for CO2 and CH4. Then on the cube, on the right-hand side, you can see the fluxes of N2 on the top side. Then on the left, it's CO2, and on the right, it's CH4. We have post-processed them at different time scales, time and space scales. You have here the grid point, obviously, for N2O, but it's a multi-year average. You can immediately spot the link with anthropogenic activity and in particular agriculture, looking at this map. Then on the left-hand side with CO2, that's for the agriculture, forestry and other land use sector, so specific grid points, and we only process the grid points of specific countries, EU 27 and the UK, United States, Canada, etc. We have the same division by countries on the right-hand side, but this time it's for the methane emissions from human activities in general, not just agriculture, forestry, and other land use sectors. You can spot, for instance, the dramatic increase in the Chinese methane emissions over the decades. It starts in 1980, while for CO2, in this particular sector, agriculture, forestry, and land use, for China, we have a CO2 budget which is pretty stable over the decades. Those are our products. They have not changed in terms of variable names, but we are working a lot, we are investing a lot in the service evolution. We want to be faster, higher and stronger, even after the games this year. And the highlight this year is that we have reached the 1 degree target that we have had over the last few years during our previous contract. We have reached it for CO2. And for CH4, 79 layers in the vertical for CO2, 34 for CH4. For N2O, it's not there yet. We are roughly at 2 degrees, but it's coming hopefully by the end of this year. Indeed, in the pipeline, we have this new resolution for N2O and 2 other resolutions that are being prepared for CO2, 90 kilometers, 79 layers, or even doubling the number of layers in another version. We are doing that because we progressively want to disappear, to see this expression disappear. It's an expression that appeared on Richard's slide and Laurent's slide. It says currently at relatively coarse resolution. Beware, Richard, at 90 kilometers and even at 1 degree resolution, we are very close to the CAMS global reanalysis that Antje presented this morning. We are coming. So hopefully this will disappear, and we are supported in this achievement. We are supported by the dense satellite data that we can find for CO2 and CH4. Unfortunately, this is not the case yet, still not yet. For N2O, we have tried many products, but they have not reached the accuracy needed for inverse modeling. And we accompany the increase of the resolution by a refinement of the prior information. When the details are not available from the satellite data, we need to have the detail from the prior information, and this is why we needed 2 additional partners. I'm starting the news after this introduction with N2O in the middle. We are releasing currently version 22. 22 means that the reanalysis ends in 2022. Indeed, we do not have any satellite data. We are left with about 100 measurement programs, ground-based sites, ship transects, and aircraft profiles. You can spot the location on the map at the bottom. Of course, there is a strong bias towards Western countries, the US, Europe, obviously. There is a bit in the Eastern Asia, the Pacific as well. The rest of the globe is not completely void, but very, very sparse. This is why we need to rely on important prior fluxes. We have revised them, all of them, using inventories or models. I'm just skipping the details here in terms of totals. This is what we have in the prior in terms of global land and ocean and sink totals, in terms of totals for the mean over the years from 1996, where we start the reanalysis, until 2022. The mean, the standard deviation, and the trend, this is the prior, and then you have the posterior. We start from the prior and we get those. The mean has slightly been reduced with an even distribution of the reduction between land and ocean, but what is the most important is that we dramatically increase the variability compared to the prior information. We more than doubled the standard deviation, and the trend as well has increased a lot, more than twice. These plots, these graphs illustrate where or how this increase of variability happens in the inversion. You have here the difference between the last 7 years of the reanalysis and the first 10 years. You can see the increase of the trends in Eastern Asia, in South America, positive and then negative values much stronger than what we have in the prior in the US and Western Europe. In terms of absolute values, so I'm not talking here about trends, but just absolute values for the last 7 years. The picture between the prior and the posterior is not dramatically different, but you can spot differences. The gradients are also stronger in space, not only in time as I explained before, but the gradients are a bit stronger. Look at Eastern Asia, Central America, Europe obviously, the United States and South America. So that's on the N2O front. Now we are moving to the CH4 front at the bottom. We have released last December version 22R2, so it ends in year 2022. As usual, there were 2 data streams, one with just the surface measurements starting in 1979, and then combining the surface measurements and the satellite data. For the satellite data, it's GOSAT, so we start in 2009. That's 1 degree resolution, first time for us, and maybe for everybody. And then going just a couple of months later, we were able to release version 23R1, again 2 types of products, surface only and surface plus satellite. But this time the satellite data comes from the TROPOMI instrument, and we have covered just the last few years with the full TROPOMI archive, 2018 until 2023. So that was our first shot at what was happening on the methane front during the last year. In the pipeline, we have the consolidated version 23R2, going back this time to 1984, when the surface measurement network really starts. And then for the satellite products, satellite plus surface measurements, we will go back as far as 2004 with the help of YASI data. This is in production, or at least being tested for the production. So that's for the end of this year. What's the added value of the satellite data? You can see it here with the comparison with the long-term emission estimates between the surface only on the left and in the middle, surface plus satellite inversion. The picture is not dramatically different. That's the same like what we had for N2O, but the gradients are stronger with the TROPOMI data. And in particular, look here, I mean the color may be a bit misleading. It's not a change of sign, it's just, or maybe a bit of, no, not so much, but actually we have a dramatic increase in the emissions. No, yeah, actually it's a change of sign, sorry. We have a dramatic increase in the emission in the eastern part of China. That's with the satellite data, but using the satellite data is not trivial. This is illustrated on the maps on the right-hand side. Top right, you can see the long-term average of the TROPOMI methane concentrations for July, and the same but simulated by the model in the middle row. You can see that the pictures are quite similar, but there is a fundamental difference in Northern Africa, and this is apparently not physical. I mean, the model doesn't reproduce it, and we don't see why we would have such a gradient over Northern Africa. There seems to be a bias in the TROPOMI methane retrievals over bright surfaces, and this is why we have to apply a latitude-longitude bias correction to the satellite data. It also explains why it takes a lot of time for us to assimilate the satellite data, because we need to know very well each product, and in particular to de-bias it directly in the system one by one. Interestingly, with the first shot at year 2023, we could see, I mean, in our first estimate, those are the colored plain lines that you can see here, time series between 2018 and 2023. in our estimates, whether surface only or surface plus tropomy, we have a peak in 2021, and then it decreases a bit in 2022 and 2023. It's too early currently to say whether this is just an anomaly along a long-term trend, positive, as is in the prior, this is the black line, or whether we have seen a peak in the total methane emissions in 2023, which would be good news, obviously. We need to wait for maybe a couple of more years to see the meaning of this peak in our methane inversion. This is a busy slide that illustrates that a lot is going on currently in the methane production chain. A lot is going on the OH field. A lot is going on the numerics, GPU optimization, the change in the Gaussian grid. Different branches are being tested, and they will progressively join the operational chain with the additional quality expected in our product. So I'm now finishing with the CO2 products. It's 1 degree resolution now, like for methane. So this allows us to have the nice details that you can see on the image. I'm trying to compete with Richard's animations shown a bit earlier. I have it 3D, you know. I'm strong. So 1 degree resolution product, and we are lagging behind real time by only a few months because we update our products driven by the satellite data every 4 months, and also because we benefit from fast information. CO2 data, I mean, those are the observations that really drive the inversion, and we are really grateful to NASA for the quality of their product. That is provided with a couple of months delay behind real time, so we jump on it as soon as it's available. Then we have carbon monitor for fossil fuel emissions, prior information that we do not change with the inversion. The tropomy NO2 product, the offline product that we use, it's not N2O, it's NO2, and we use it to disaggregate carbon monitor. That's something that we just discussed a few hours ago with Juho. That's a topic for collaboration in the future with CAMS 261 or 62, I'm not sure of the number, where we could really collaborate because we have the same target basically in 2 different services. GFED for prior fire emissions, Copernicus Marine Environment Monitoring Service for the prior ocean fluxes, and ERA5 obviously for the horizontal winds. As a bonus, we provide maps of displaced carbon for comparison with the inversion data that we produced with the UNFCCC data. That's a legacy from the COCO2 project that we carry on within CAMS 255 bis. As I explained, we are quite fast. We try to be behind real time by just a few months, and we have invested a lot in the numerics of our system. Over the last few years, we have tried to replace our advection scheme on rectangle grid, to move towards hexagons that provide interesting features, interesting properties when you move towards the pole. Finally, we are seeing the end of the tunnel, and you can see here a forward simulation after 15 months with the 2 grids. And actually, these 2 snapshots are very consistent with each other, even though when you zoom, you have a very different representation of the grid cells with the 2 grids. We are testing it in a full environment, operational environment. Sorry, the titles are a bit wrong. We are here at 90 kilometers and 79 layers. These developments on the hexagon grid allows us to directly test the feeding of our inversion system with the ERA5 data without going through the LMDZ general circulation model. We just needed a bit of help from our friends at ECNWF. And in the end, you can see here, once again, after 12 months of simulation, you have something which is very consistent between the 2. But on the right-hand side, you have something that can be generated much more faster than using or going through the LMDZ model. This this is just the beginning. We need to work a lot on that, working on the adjoints. There are concerns about the nonlinearity of the IFS tracer transport convection model. And in general, we are porting all our inversion system on these CNWF computers, not to do the production, but to see whether there is a mutual benefit in having our codes closer to the heart of CAMS. We are supported by an improvement in our prior information. We are doing this in particular for land surface modeling with the Orchidea model, and soon we will have the capacity to generate in near real time CO2, N2O and CH4 emissions at 0.5 degree resolution. Don't be fooled by here the coarse grains here, it's just for an illustration. We are working at 0.5 degree resolution, and that will feed the 3 production chains in near real time. That's for the land surface. And for the chemistry, we have also KNMI working on this. They joined the project a few months ago. We need chemistry for CH4, for N2O, and to some extent for CO2. This is being developed in a near real-time fashion by KNMI using the IFS model. You have here some sensitivity studies to generate the CH4 loss rate with the IFS, and here the long time series with the OH. I'm just finishing with this slide. I mean, it's the usual CO2 MVS picture that was shown by several presenters, including Richard this morning. This is a strong motivation for us. We have no mandate, of course, and it's too early within the CO2 MVS, but we think that our tools are not only scientifically excellent, but also numerically very efficient and getting more as time goes by. And we hope to provide cornerstones for the future CO2 MVS with the tools that we are currently developing for CAMS. And with this, I'm done.
Thank you very much, Frédéric. In the interest of time, I'm going to ask to defer questions to the lunch break. We have one more presentation to go. Johannes Kaiser will talk about GFS, and he promised to keep it short, so we can finish more or less on time.
Yes.
Thank you.
My apologies for taking you from having lunch on time. I have only 3 co-authors. It's a small project outside ECMWF. It's only Sisha and myself working on the developments of GFAS, so I'll try to be concise in this presentation. Laurence has introduced the whole CAMS system with a variant of this slide, and the question is, where does GFAS go in? And it fits quite nicely. It does do assimilation of satellite observations of high radiative power in the central global fire assimilation system and computes fire emissions, which are then being used as lower boundary conditions by the global and the regional air quality systems of CAMS. And Frédéric, we have to talk about what you need to use GFAS for your inversions. There are currently 2 versions of GFAS in production. On the right you see an overview of the distribution of fire emissions in last year. On the bottom you see that this GFAS version has been consistently produced since 2003, and a comparison to the GFAT data which Frédéric used, and which are obviously going back to 1996. GFAS is using MODIS observations on the 2 satellites, Terra and Aqua, as input. It's producing 0.1 degree resolution, 40 smoke constituents, and estimates of injection height. The 2 versions, 1.2 and 1.4, differ in that the former produces daily updates and is publicly available on the ADS, whereas the latter is updated every hour and with a corresponding time resolution, and is used internally in the CAMS systems. during the last year, our main achievement really was to achieve service continuity, because this dependence on the two MODIS instruments is going to be over. We have to overcome that in the future, because they are running for more than 20 years, and it's running out of fuel, and they are planned to be deorbited. So what we can use as a replacement for the MODIS Aqua observations are the VIRS observations on a series of NOAA satellites, and so Suomi NPP was the first of those. The advantage here, these satellites are sampling the peak of the fire diurnal cycle, and we have done dedicated calculations of the uncertainty and of the biases to debias these observations, and then now we are assimilating them in GFAS, and we have first tests have been positively evaluated by our colleagues from IFS Compo. To the right, you can see what this does with the emissions. The black line is the current GFAS 1.2 based on MODIS, and the red line is when we add VIRS to the equation. It's 3 months of fire radiative power over Europe, summer months in 2022. And you see that it's not a fixed offset, but the VIRS elevates the emission to a certain degree. Replacing Terra MODIS will require the Sentinel-3 observations, which are in the morning orbit, and this is still work that's ongoing. The other big improvement that we did was replacing the spurious signal mask, and the top here you see the current mask of spurious signals, which is based on an analysis of persistence in the observations, but you see it's a very coarse resolution. And now we have derived a new spurious signal mask with a much higher resolution, 0.1 degree. That's why you don't really see anything at the bottom. But those masks are also temporarily resolved, one mask for every year. And here's a zoom into Europe with the new mask, and now you get to see the oil fields in the North Sea, you get to see the volcanoes in Italy, and you get to see this tiny yellow speck up there in Sweden, where we had feedback from the Swedish air quality modelers that they had a spurious plume in their forecasts in that location. And that is the location of Boliden Rönnskär copper smelter. So we were really happy to see that our generic approach did include this. Other locations we see in there are like French nuclear power plants, and you can. It's quite fun to zoom into that. So that's a zoom in of the yellow speck up there, and so everyone can see it in the back as well. And you see that's the resolution of the GFAS grid. So. Applying the new spurious signal mask removes 9% of the global overall FRP signal. So that's quite significant. The previous mask did 5%, so we have a quite significant change there even in the budget. And the assimilation of VIRS together with this new spurious signal mask is now running as an e-suite at ECMWF. So it's being tested, and I said already tests with IFS Compo were positive as so first tests as far as we could see. From the ongoing developments, I just want to highlight one. Last year we had in the Code for Earth project activity of ECMWF, we had one project where a team of students looked into forecasting the fires for the next 24 hours based on the actual fires we have now. So one of the shortcomings of use of GFAS and CAMS has always been, what do we do during the forecast? We assume persistence. And if we assume persistence for the fires, we get these mean error, root mean square, and correlation here. and the team has tested a number of different approaches, a linear regression, a regression tree, and an ensemble of neural networks. So those were deep neural networks, and really the neural network was the one that bet all the others, that showed the best results. And this slide sort of shows what it's doing. So this is 24 hours. The present is in the middle, and the input for the neural network is the black line. That's the fire emission in GFAS. And then it does get meteorological data, 3 different meteorological fields for the last 24 hours, but also from the forecast for the next 24 hours. And then the neural network produces the red line here as the forecast, and then in hindsight we can compare it to the black line from GFAS, which is then produced in hindsight. And that's where the statistics come from, and in this case you see it dampens down the fires, and when you look at the green dotted line, that's the soil moisture. There's a jump right at the present, which is driven by a precipitation event, which is obviously dampening the fires, and that's the type of signal they're catching. So this is very promising, and we want to keep developing that. In terms of outreach, we've contributed to the NOAA BAM State of the Climate Report. Here are the anomalies. Here are time series of 3 different regions which show very typical fire behavior. So one is over Canada, you see the huge fire event, and that's an increase of intense forest fires, so intensity and frequency of forest fires. Number 2, in Northern Hemisphere Africa, there is a downward trend which has been linked to the expansion of agricultural areas into savanna areas. And number 3, in Southeast Asia, in Indonesia, there has been elevated fire last year, but it's been an El Nino and it's much less elevated than during previous El Ninos. And there you can see the effect of political measures of the Indonesian government to curb the use of fires in the plantations. We have contributed to the European State of the Climate Report. The interesting thing here is when you correlate the fire detections in red with the soil moisture again, you can really see the link between the meteorological conditions and where the fires occur. So in interpreting why it's happening, that's where the information goes. In interest of time, I skipped the other 2. Second last slide. Fire monitoring is a really key element of the CAMS activities for communication and press. And a majority of the CAMS media inquiries and data requests relate to wildfires and the atmospheric composition and air quality impacts of those wildfires. So that's really one thing which gives a lot of visibility based on this very basic data at the front, and then with all the processing on top of it. And that sort of gives the visibility, of course, then helps to also raise the visibility of other CAMS activities. This is a comparison of emission inventories. The take-home message is they differ vastly. Uncertainties are huge. The bottom left, the highest difference is here, the green, that's peat fires in Southeast Asia, where only GFAS is representing them, probably overdoing it though, whereas the others don't. And my last slide. So what are the remaining challenges and next steps? I think you can really split it into 2 big areas. One is improve the spatio-temporal distribution of fires, and here that's done by assimilating more observations, in particular from geostationary observations, where the CAMS 264 project is also producing FRP products from geostationary satellites. of course, using more of the polar orbiters as well. But to do this, you really need to look at the bias correction, and you can use the forecasting with the machine learning also to fill those observation gaps. And the other is to improve the emission source strength by using the information that we get from other inventories, from inversions, from online inversions, and from feedback from users. And so that then comes, of course, a lot, the validation done by CAMS can really feed back information into this aspect. And I said other emission inventories, we're looking into published field and laboratory measurements, of course, keeping track of what emission parameters are being published. But in the longer term, this should really also link to modeling of vegetation, fuel, fire, how the fuels build up, what the fuel state is, what the carbon stocks are, and what type of fire is there. That's like smoldering versus flaming. So I think in the long run, we've got a very big topic at the last row there. And now, time for lunch. Thank you for staying.
Thank you very much, Johannes. Again, questions during lunchtime. We are breaking for lunch. We are also asking you to please come back at 2 o'clock because we've kept the best for last. We're getting a really exciting session with all the new developments supporting the further improvement of the service. So please come back at 2.
No, everyone wants to.